Steve Jacobs, and I represent Oregon Independent Science. I think that's what it's pretty close.
I'm Carl Schreck and I represent OSU.
Lance Krusik with NOAA Fisheries, the federal representative.
Travis Mackey representing Oregon Tribes.
Michael Banks, I'm a professor with OSU based out at the Hatfield Marine Science Center and what's called the Coastal Oregon Marine Experiment Station. And I've been researching hatchery wild issues for coming on 30 years now. And I've been privileged to be part of one of the projects here.
I'm Dwight Collins with the Oregon Salmon Commission.
Jen Frischuk, manager of the OHRC.
Seth White, OHRC and Oregon State University Fisheries and Wildlife.
Scott Starkey, chair, and also represent forest products industry.
I'm Carrie Tarpita and I work for the Department of Fish and Wildlife.
Pete Grindike and represent Fish Habitat Restoration.
Ed Simon, agriculture.
Jack Smith, recreational anglers.
And
I'm Claire Couch, a researcher at Oregon State. Kayla Kelly, I'm a master's student at OSU.
Michael Blumen, I'm a professor at OSU.
Yeah, contact, just
audience.
I'm Andy Dittman. I'm with NOAA Fisheries at the Northwest Fisheries Science Center.
Okay, thank you. How about online? Can we?
I'll call through the names. Seth.
Yeah, Seth Eisenberg, representing Wild Fish Conservation.
We don't have one. 1 second. We don't have audio, but we do see that you're there.
Yeah. Let me know when you can hear me. I've come off mute on both.
No, okay. I think you're good now, Seth. Sorry. Can you
Yep.
go ahead?
No problem. Yep, you can hear me now?
Yep.
Okay, Seth Eisenberg, representing Wild Fish Conservation.
Okay, thanks. Selena.
Hi, I'm Selena Happel. I'm the head of Fisheries, Wildlife, and Conservation at OSU.
Okay, Bill. You're muted, Bill.
You're on mute, Bill.
Sorry about that. Bill Lansing, Coos County STEP.
Morning. And last but not least, Mimi.
My name is Mimi Obley, and I'm a master's student at OSU.
Morning.
I guess that's it. Thank you. Like note that if you look at the agenda here, we do have a tour scheduled right after lunch. I mean, often we had the tour kind of optional at the end, but most of us were in a hurry to get out of here, so we missed the tour, and it's a good opportunity now for everybody to visit the facility again, and Jen's going to take us through what's going on. Thanks. There's another thing in the format today will be probably a little bit different. Seth and I have discussed this, and we've kind of some format changes in the research where we're actually asking the researchers to make recommendations and kind of let us know about what discoveries they may have made that are applicable at this time. So things are just a little bit different, but I think it's going to be very interesting and looking forward to it. With that, go on to the minutes. Did everybody get a chance to take a look at the minutes from the March 15th meeting? Are there any discussion or any questions or changes? I guess I have one though. If you go to the second page, correct. We're on the chair's closing statements on the end of the meeting. It says we have 3 board member term expirations coming up on June 30th. Scott, Lindsay, and Jack. Board members can serve 4 consecutive terms and can be appointed by the director of ODFW. That's actually not right there. The term is 4 years, but they can be reappointed, so there's not a four-term limit. So that the minutes should change, so instead of saying members can serve 4 consecutive terms, it should be the term is 4 years and can be reappointed. Okay, thank you. Which brings up a little discussion we'll probably have for another meeting, that we serve, board members, we serve 4-year terms at the pleasure of the director. So Kirk can us at any time or extend or reappoint us. But there is no term limit. For the chair position, like the position mine now, you can serve 2 consecutive 2-year terms, but and the board members are 4-year terms and can be reappointed, but there is no limit. But perhaps there should be a limit on the number of terms that we serve. Some of us, a couple, 3, 4 of us are in our 3rd or 4th term now, I think. And there's some good things, just like Congress. I guess it's good to have some history and continuity over the years. And on the other hand, it might be good to have some more new fresh blood coming in. So it's a topic we should consider, and we'll probably bring it up in the future. We can change that and put it in the charter by a vote of the board. So I'm not sure which way we want to go with it, but it's just a topic we need to discuss in the future. Like a motion to approve the minutes with the change. Have a motion.
I think that motion.
Have a second? Okay, is there any opposition to the minutes with changes? If not, I guess we can just record it as a passed motion. Thank you.
For the record, we're recording, and that was Jack Smith made the motion and Ted Simon second.
With that, we'll move on to Seth or Jen.
Yeah, thanks, Mr. Chair. Thank you, members of the board. Good morning, everybody, visitors, researchers. Yeah, we'll just start the day with a couple of introductions because we have an exciting new sort of crew of people that are on board now, both at OHRC and Oregon State University. So Jen will go first, and she has some exciting news about staff updates here.
So Zach, our new senior tech, he started April 1st. He's been great. He's on vacation. He's back later this week. Last week I hired a temporary technician, Nathan Spalding. He graduated from OSU. And so he's out working. And he's here through the end of September, kind of to help backfill. We have more tanks than we've ever had out there, full of fish right now, and less staff than we've ever had. And then I have Jessica is an intern. She started this morning, and she's out there doing work also. She's been on here as a volunteer through the spring, so she knows a little bit about what's going on. And so she's here to do 360 hours or something by the end of August. So she'll be here a lot. And then we're doing interviews for our limited duration on Thursday. This is the 3rd round of interviews with like full close the thing, start over from scratch. Really struggling to get somebody to accept a 1-year position out here. But hopefully this time we'll get somebody. Yeah, so then I guess, yeah, we did get hosts at the beginning of June, and they're here through the end of July. And then that is all for hosts. I thought I had somebody lined up, but I didn't.
How long is a limited duration, Jen?
Hmm?
How long is a limited duration?
It depends on the position, but ours is going to be a year. And then there's the potential to extend it if if we need, or if, so it's our permanent position has been reduced to a limited duration. And then if we're still kicking around in a year and can still do good research on here, then we'll go ahead and extend that. So it's basically a minimum of a year.
So then you'll have 2 additional full-time people.
Yeah, so it would be Zach and that person. And then for the summer, we have Nathan and Jessica, and then after the summer, it goes back to just the 3 of us. Yeah.
What was the rationale from changing from permanent to limited duration?
You would have to ask Sean Clemens that.
Okay.
It was above my pay grade on that
Okay,
one.
all right.
Yeah.
You have the Fall Creek, the Fall
Yeah,
Festival,
yeah, so we are gonna plan on doing the fall festival. Michael's gonna do leather
and I'll
working
be
for
doing
us.
the other one.
Yeah, and so that'll be in November. And we'll plan that sometime and make that happen.
Planning on planning.
Yes.
That's a great thing.
I think there's notes on this pad of paper about it, but yeah, I'll give a full update, I guess.
Yeah.
Yes. So I can give you the full fish numbers and what's going on out there as we walk around, and then anything remaining at 2.
You'll be okay staff-wise.
Sure. Yeah. We'll kind of do what we've been doing and prioritize fish and research, and you know, maybe there are places that are not as visible that will not get as much love as they need. So that's definitely not a great way to run a facility, because then those places in the background are just going to break down, and the repair will be more than it would have been had we just kept up with it as it goes. But I mean, it was just Nathan and I yesterday, and we spent 2 hours doing research for the fit study, and then 3 hours or 4 hours cleaning tanks, and got half of them done. And then fed fish for a couple hours, and the day was over. And that's all that happened. It's currently not possible to do anything more than care for the fish with just 2 people, which is why we've got the temp and the intern temp of us.
And so everybody knows Jen's been working like crazy over the last, year and a half. Right?
We haven't had a tech since November, and we haven't had, we had a senior tech starting in April, but between the middle of December and the middle of January, there wasn't anybody here but me. And then we had to work out of class for 3 months. And then Zach came on. So lots of training, lots of teaching. But these guys are picking it up really fast, and it's really nice.
Let's go start that presentation.
Oh, we have a presentation.
Well, I've got like a presentation that has all the materials. Yeah. All right, continuing on the theme of new people, onboarding new people, and also this topic on the agenda is about some of the, just thought I'd give a quick update on some of the extramurally funded research that I do, because as you know, part of my job is a faculty member at Oregon State University. So I have the OHRC related work, but then I have this whole other part of my life that I do work, and I thought I'd give you just a really quick update on kind of things that we're doing there. So the second one. But first, some introductions. So we actually have 2 in person and 1 online. Just hired on Ashley Sanders as a faculty research assistant, and Ashley just completed her MS at Oregon State just about a week ago. So congratulations to Ashley. Did you want to say something about kind of your position here at OSU?
Yeah, I just started, so not too much onboarding stuff so far, but going to be helping out with a few with a master's student and a PhD student, and then doing kind of odds and ends, starting with the lab for stuff. So yeah.
Glad to have
Excited
Ashley.
to start.
Thanks.
Yeah.
And then online we have Mimi, and Mimi is still a master's student with Dr. Bluen, but assuming everything is on track and everything's good to go, I just got a thumbs up from Mike. Mimi's going to be coming on in the winter of 2024 or in January 24. So hi Mimi, do you want to say just a couple words about your project?
Yeah, so as Seth said, I'm finishing up my master's, which was looking at like hatchery reared steelhead and variation in size among families. But starting January, I'll be focused on the olfactory project that's going on, especially looking at different hatcheries and the potential for straying in those areas.
Yeah, excellent. Thank you. And then also in person, we have Kayla Kelly, who has a bachelor's from University of Central Florida and just came on as a master's student at Oregon State University. And she'll actually spend just a minute describing her project in the Upper Grand Ronde. So yeah, go ahead, Kayla.
Hi, everyone. Yeah, so prior to living in the Pacific Northwest, I did a lot of my research on razorback sucker and Colorado pike minnow in the Colorado River, primarily on fish passage stuff. So it's a nice change to be up here. For my project with Seth, we're going to be looking at spring Chinook salmon dispersal in Catherine Creek, and based on spawner origin, riverscape conditions, and utilization of restoration sites. How this relates to the Oregon Hatchery Research Centers, we're going to be looking at the differences in dispersal among wild and hatchery fish. We started sampling adults in this summer, and we're going to be sampling juveniles in 2024.
Yeah, excellent. Thanks, Neil.
Catherine Creek is where?
It's near LeGrand.
Okay, thank you.
And that project is funded by Bureau of Reclamation, and it's really highly collaborative. It's the kind of research that we couldn't do if it was just us out there. It's the Umatilla Tribe, Oregon Department of Fish and Wildlife, NOAA Fisheries, and Columbia River Intertribal Fish Commission are all like deeply entwined in the project. So yeah, we're quite excited about it. We'll give you updates along the way.
Seth, how's the Bureau of Rec involved with that? Do they have water projects there or something?
Yeah, because the Bureau of Rec focuses a lot of their restoration efforts in floodplain areas. They want to know, are fish actually using those restoration projects, and at what spatial scale? Like, where should they place those projects in relation to where the spawning happens? So our project is going to be tracking individual juveniles, where they come from the red. So we'll know their dispersal.
Got it.
And they're giving us the money.
Well, that's always good.
Okay, another project that we just submitted a statement of interest in, and we're hoping to get an invitation to submit a full proposal. This is evaluating the risks and benefits of hatchery programs for Chinook salmon and their freshwater habitats in the face of climate change. And we are hoping to get some pilot studies started, either out here at OHRC or perhaps at the Aquatic Health Lab at Oregon State, looking at basically snow drought, so conditions where you have really low flow and high water temperature, but also you can have higher flows and higher water temperatures, and looking at how hatchery origin and natural origin fish perform in those different environments, and also working out a non-lethal physiological stress assay that I hope Carl is pretty excited about, because if it works out, I think we can apply that to the surrogates project as well. And this is a collaboration with CRITFIC and ODF&W. And if we get that funding, we'll be recruiting a MS or PhD student.
How long is that project?
Sorry?
How long is the funding period?
It's a 3-year funding, yeah. So, and it wouldn't start until late 2024. So we'll cross our fingers and keep it posted. Okay, That's all I had on that topic, unless there was any other questions there. Okay, moving on. Mr. Chair Starkey mentioned at the beginning that we were going to talk about management recommendations. So that's kind of the theme of the morning meetings. I wanted to kick it off really quick just to kind of get us in the spirit of the discussion that we can have after, the board members can have after the presentations. But essentially, one of the duties of the OHRC board, as we've been talking about, is to make management recommendations. So we thought it was a great opportunity now that we're at the very tail end of the OHRC Research Fund projects from 2021 to 23. Those are ending as of the end of this month, with the exception of the ones that are continuing in the new round of funding. So we have the opportunity, we have kind of a captive audience with our researchers here that can kind of help us get that started. So I invited them to come speak today to give the key findings of their research and kind of summarize what they've learned, but then also give us what they perceive as the management recommendations. And I consider these kind of like draft material at this point that the board would have to work on over the next sort of few months in order to put those into the annual report. So I just have a couple of slides, but I'm going to kind of back out of the conversation because I think it's a conversation the board should be having amongst themselves about how they want to do this. But I have a couple of ideas on how we can get started. I have this up on the screen here, wet paint. A lot of you know that my wife is an educator. She teaches kids. She's a music teacher, and she has big groups of kids coming in and out of the classroom. And so one of the walls was getting painted, and there was a sign that said wet paint. And she told one of the students to, make sure she reads the sign that's on the wall. And so the student went up and she read the sign, and then she immediately put her hand on the wall. So what was missing from the sign was do not touch. Yeah. So drawing the analogy there, this is a key finding. The paint is wet and the management recommendation is do not touch. So very simple. But of course, as scientists, we like to make things really complicated. So researchers are evaluating whether the paint has dried. If so, feel free to touch. So there's a tentative recommendation there. Just a couple of materials as background. The Oregon statutes and the legislature have specific language in there that the board will make recommendations regarding current hatchery management practices based on the research projects. And the based on the research projects, I think, is a very key point of that. We're not just making recommendations in general, but what do we draw from the research that's happened here at Oregon Research Center? And then in our most recent annual report, we listed this as one of the activities that we would do, develop and or refine management recommendations based on OHRC research. So I have an example here. This is a hypothetical example that Selena actually started earlier on, and we kind of workshopped it a little bit, but just to get you in the spirit of kind of how to think about key findings and how those translate into management recommendations. So, the one that's up on the screen there, global warming will cause major disruptions in the world's economies that are dependent on floodplain resources. Farthing 2019 showed that the cost of flood damage and reduced fish harvests have been increasing 12% per year on average since 1979, a rate greater than economic growth in most countries. So that's a pretty general finding. A recommendation that you could make from that is that the findings warrant preemptive measures to protect floodplain infrastructure in addition to immediate financial investments into climate resilient fisheries practices. So that's a pretty general recommendation. Researchers are always improving their research and working on the next thing, and sometimes those findings are actually in progress. So I've kind of got that too. So for this hypothetical example, researchers are currently evaluating whether poor quality of spawning habitat is limiting fish productivity in climate impacted watersheds. That's unpublished data. And the tentative recommendation is, if so, financial investments should be directed towards habitat improvement and protection of spawning grounds. So just kind of pointing out the difference that some conclusions are final and some are tentative. And so kind of approaching it from that spirit is, I think, the way to go, the way that we want to approach this. I've got a proposed strategy and a timeline to develop the management recommendations. And I think for this discussion, I want to just show you this really briefly, and we can come back to it in the discussion that we have after the researchers have presented their presentations today. So, I propose that the PIs deliver a presentation with the draft management recommendations at today's board meeting. And then I would recommend that OHRC board form something like a working group or a subcommittee focused on the management recommendations and have one meeting prior to the September board meeting. And then at that September board meeting, present a list of the draft management recommendations to the other board members, and then meet once more prior to the December 23 board meeting, and then present the final management recommendations for board approval at December 2023 board meeting. And then that would lead to including those management recommendations in the OHRC annual report that comes out in February. So I think this was just my idea. There could be different ways to do this, but I thought I would just kind of throw it out there as a template, and the board can discuss whether they want to use a different strategy or what the nuances might look like. We basically have on the agenda all the way through lunch to hear the presentations, and then some open period for discussing the management recommendations. And that could be a discussion of the recommendations themselves, but it could also be a discussion of the process that you want to use to come up with those recommendations. I asked the presenters to give about a 10-minute presentations, and a couple people pushed back on me that they needed a little bit more time. So I think that's totally fine. Yeah. Andy's got 84 slides.
No, I
yeah.
had more time, I would have.
Yeah. But yeah, so we don't have to be too rigid on time, but I think if we give every presenter about 15 or 20 minutes, including the questions that would come after the presentations, that would leave us a little bit of time for discussion prior to lunch. Yeah.
So, Sid, I just want to have a bit of discussion about how I respond to this time frame that you have there. I think it's really great, and obviously as we think about modifying hatchery practice for different outcomes, that's a big kind of engine to change. But as you mentioned, some of our studies are very much ongoing, and in my case, 2/3 of the million fish that we created to test this out are still having, expressing that. And we're only going to really be sure and have a concrete statistical support to say, hey, this is really a strong effect, and it's worth all this change in about 2025 or 26,
yep. Which
is beyond that time frame. And I don't know about how the other projects are, but I think we should. I've already started sharing with board stakeholders, because I think it's a big project in terms of conscientizing people. But we want to be sure, before we move the mountains, we want to be sure that we do that for a good reason, or prudent reason.
Thank you, Michael, for that. Yeah, I completely agree, and I believe we're in the same boat in the olfactory and printing projects, because those were designed as long-term projects, and we also have fish out at sea at about the same schedule that
Yeah,
you
we're
do.
on exactly the same schedule.
Yeah, so we're waiting for the data to come back in, and we don't want to make preliminary conclusions or recommendations based on answers that we don't have yet. But I think we can make those kind of tentative conclusions. Like, we can say, if this works, here's what kind of management change that might lead to. We need to be very careful about the language. OHRC has short-term research that has immediate management recommendations that we can make. You know, we'll hear about thiamine and other operational research. So, but thanks for bringing that up.
Well, I mean, the other thing is that I'm finding that there's a very enthusiastic audience out there, which is actually really exciting. But as I present to broader stakeholders, there's a lot of people that want to sort of contribute and mention other studies, and so it's timely to begin the process now, but we need to proceed deliberately.
I totally agree. Thank you. Any other comments before we jump into the presentations?
Well, along those lines, there's always something that you can draw out of it. Maybe it's how the techniques that you used, and maybe there's some information there that would be helpful to put in this year's annual report. Not necessarily the conclusions, but what you've learned thus far.
Absolutely, sure.
When we talk of management recommendations, how far beyond the center are we looking at recommendations? I mean, is it into the field? Is it at the hatchery level? I mean, it's where are we going with this management? How far, how big is that circle?
That's an excellent question that brings up a really good point. I mean, every researcher that writes a paper, usually there's a management recommendations section, and you put some kind of borders around, in which type of situations would these recommendations apply. Olfactory imprinting, for example, like we may see limited success in drawing fish back using the amino acids, but we know that other studies have used other chemical compounds and have managed to draw fish back to hatcheries. So, we don't want to base the entire recommendation on our research alone. We have to consider the context of the other studies and the other information that's out there. That's why I think, having a series of meetings and workshops to discuss these very issues. I hope that we can continue to draw from the researchers and bounce these ideas off of them so that we can get their kind of stamp of approval on what comes out of the OHRC. And I'd like to be involved and can help kind of guide that process as well. But it's very tricky. What you bring up is really nuanced and difficult.
But we look at the research and we make recommendations, but we don't set policy, or we don't have the authority to implement anything. So we make the recommendations to ODFW, and then between ODFW and the Fish and Wildlife Commission, they decide whether they want to implement what recommendations we make. But it's our obligation to do that, to make some recommendations. We haven't been doing a very good job of it in the past, but whenever we can come up with some sort of confidence enough that we can make a recommendation, we should be doing that. And going into the annual report, then the legislature reads that, and they can see, oh, well, OHRC recommended ODFW that these things be implemented.
I would think that we need to stay as broad as possible. A recommendation falls outside of the purview of the OHRC, that's totally fine. In other words, we maybe would discover Corningware trying to cool down a spaceship, something like that. So
But we've been around for
we maybe
13 years
we'll
now.
find something
We
that
should
has
be-
nothing to do with the mission of the OHRC, but it's really important elsewhere.
Thank you.
Okay. I guess any other comments on that process? All right, Michael, without any further ado.
Okay, well, it's my pleasure to report to you on the many different things that we're doing in our project. And as you know, besides funding the long-term project in improving the fitness in hatcheries through emulating wildlife selection practices, we're which are made. So through your funding, been working on an automatic fin snipper that we hope will sample thousands of fish in a hatchery per day. Because we need to do that every fall through 2025 as part of our project. So I've reported to you folks a lot on this research, and I've tried today to make it more of a overarching overview and to end up with some management recommendations. So here we go. In terms of background, hatchery release numbers have been constrained because of the finding by others in this room and actually among 4 different species of salmon that generally hatchery fish draw down the productivity of native fish if they should spawn with them in the wild. There are different opinions about this, but the conclusion is that really that is an issue, and it's about a 50% drawdown in fitness. So we have this Oregon Hatchery Research Center goal number 2, how we may develop approaches to manage hatchery fish that conserve and protect natural fish more clearly. And this project obviously is related to that specific goal. And I just wanted to step back in time, basically before this board even existed in 2013. Senator Krieger asked David Noakes and Michael Bloom and myself, what research do you think should be done at Oregon Hatchery Research Center? And given my interest in this issue with hatchery fish drawing down the fitness of wild fish, should they spawn with them in the wild, I replied and said, well, let's see if we can overcome this fitness shortfall of hatchery fish by increasing their productivity. If we could learn how to mate them using wildlife mating strategies. And very fortunately, the board went and got funding, and we've now continued this research to address this question. So why did I think this? Why would wildlife mating, mate choice in hatcheries help their fitness? Well, it's a key sort of understanding amongst biologists that the key to more and higher quality offspring, one of the factors behind doing that is to actually have a hand in choosing who you mate with. This is something that has been part of our knowledge since Darwin about 150 years ago. And if you look at studies over the last century, distributed all over that time, in all different creatures, it has been shown that if you allow individuals to choose their own mates, they have very much more successful offspring than if you decide and force them to mate with whoever you want them to mate with, which basically is the current practice in hatcheries. There are about 30 current studies, and the range in fitness in those current studies, the fitness increase for wild or chosen mate is the difference in effect averages out to about a 40% increase in fitness. So my thought was that this could maybe accommodate and reverse that 50% drawdown of hatchery fish should they spawn in the wild. So what have we done since 2016? First, we did a complete review of mate choice in salmonids, that's published in 2019. And then we did an extensive genomic study of all the potential markers, basically 15,000 SNPs we isolated from a past pedigree where we found and demonstrated statistical support for about 200 genetic markers associated with mate choice in cohort, as well as the 2 different ways in which those markers are selected. So in some cases, moms and dads or dams and sires choose a different form of the marker than they have themselves. We call that disassociative mating, or they choose the same marker as their mate. We then developed and tested a rapid assay to genotype cohort broodstock on the fast track in the hatchery, and a computer program that allowed us to select mates very efficiently that most effectively represented wildlife mating partnerships. So the assay is something we can do in about 14 days, and the actual program really on hands in the hatchery can determine how best to combine, say, 10 males and 10 females on the spawning rack within about a minute. We use these tools to test wildlife and random mating at Sandy Hatchery in 2019, 20, and 21. So it's a nicely replicated, repeated study over those years. And then, of course, those fish were released into the ocean, lived their lives, and then we have sampled them. And we are beginning to sample them, start in 2021 as they return. And they come back in the thousands, actually. Last year, we sampled 7,000, the adults from 2019 spawn and the jacks from the 2020 spawn. And we'll do the same in November, December this year, and November, December 2024. We co-wrote a public press article about this research that I believe I've shared with you guys. We've developed a tool to automate genetic sampling of thousands of fish, and I'm going to finish this slide to show you our last prototype that actually is successful. We began to determine the results, and I'll show you some of those in a moment here. In terms of management and what I was talking with Steph about earlier, we've also begun to share our findings, merits, complexity of our approach to more broader stakeholder groups. I spoke with the annual meeting of the Oregon Hatchery Managers last July here in Oregon. In December, I spoke at the American Fisheries Society meeting of the Fish Culture Concepts in Portland. That drew about 300 people there, hatchery managers from all over the country. Then also at AFS in Eugene, Jen and Seth and I all featured in a special session there. And then I plan to also present at the National American Fisheries Society meeting at Grand Rapids in August this year. And as I mentioned, I'm getting a lot of enthusiastic response from the audience there. So just in terms of some of those activities, that looks really nice and clean. That's Dave sampling one of the cohort adult returns from our 2019 spawn. That's not quite a completed machine that we hope to facilitate this, but it really much helped us. Basically, on that day, we sampled 2,500 fish, lifting each one up by ourselves into that machine. It was very nice that you could actually operate the punch just by a foot pedal there. And it looks lovely and clean, but I tell you, by the time we got to the end of the day, it was a lot more slimy and messy than what you see there. I have two slides here from some of the development of the automated fin sniffer. That's Spencer. He's an undergraduate from College of Engineering. He is really into programming, and his idea was that we could use an array of lights underneath the device to then be able to trace out the position of the tail. And then this other student was working with a contraption rather like a 3D printer to position a punch over wherever Spencer had determined the tail was. These guys worked really hard, and I was very delighted to work with them, but we found that the program to determine the position of the tails and to integrate that position with the 3D printer to then position the punch was all too slow. So this prototype basically told us that we need to think of a more clever way of achieving this. And I'm about to show you, well, at the end of the talk, I'll show you this. Okay, so back to the main activity, the spawnings, where we tested wildlife versus hatchery, random spawning in the hatchery in 2019, 20, and 21. Just a brief reminder on that. Basically, day one, we go out to Sandy Hatchery, where all the fish have returned. And here's Josh crowding the broodstock up into a cage that then raises a subsample of those fish up above this tank where they are euthanized with carbon dioxide. They become calm and you can grab them out, take them over to a measuring trough and actually tag them with a floyd tag. Of course, we take records of those tags and take a fin clip. So that gave us DNA from every single one of the broodstock. There are about 500 that we used there, 200 males and 300 females. And we took that DNA back to Hatfield and genotyped them all so that we could return 14 days later for the actual spawning. So now we are equipped with all the genotypes and the program that I told you about to very efficiently determine among the males and females how best to combine them to represent, or most closely represent, a wild-like mating strategy. So just in terms of the setup, these are the females. You can see their tags there, so we know the genotypes of each of those females. They now are assigned with their best choice of a wild-like male that matches the genotype of the male and the female to best represent strategies that we observed in a wild pedigree. And these are the random males, because the experimental design basically is to divide the eggs of each female into 2 equal halves. One half is bred to the random male, like is typical for a hatchery, and the other half bred to a mate choice male chosen using that computer program. So what's really neat about this is it's the same genetic background. There's no unfair treatment, and all the fish were reared in the same rearing conditions. So there's very little different treatment effects that we have to worry about. So here's Charles, that one you can see actually underneath the fish, there is MP for mate pair. That's the actual genotype chosen male spawning those eggs, and the beaker on the left will be for the random male. So those fish were then reared and went out to the ocean, and they are now coming back. And here's the first results I have to present to you. So for in 2021, we got 1,300 jacks coming back. And of course, we want to see how many of them resulted from the half of the eggs that were random mates or the half of the eggs that were mate choice chosen. We got DNA and data from about 95% of those jacks. Parents identified in just about 1,000 of them, or 80%. And fortunately, the results were to our favor. So 52% of them were from mate choice fathers versus 48 from random fathers. It's about a 5% difference. So not very strong, but actually, if you rank the returns by what we call the alpha males, the ones that had most of the jacks returned. This is the top dozen alpha returns, and in blue, those are the ones sort of highlighted as mate choice fathers, and red are random fathers. And you can see that in the second column there, 8 out of the top 12 alpha males are mate choice males, and only 4 random. So looking at the top line there, for example, female 15, the mate choice male had 47 jacks come back, and the alternate random male had only 4. The next one, the tables were turned the other way. The random male had 43 returns come back, and the alternate mate choice male had 25. So looking at all those numbers and asking the question, how much more did the mate, what's the benefit of using mate choice? Amongst those 12 there, the mate choice parents had 102 more jacks than the random male. So that's looking very, very promising. So that's just the results for the top 12. This is the results for all the fish, all of those 100 and I think it was 1,223 that we got usable results from. And you can see these are box plots, and at the bottom there you can see they have a relatively comparative mean. But what's really different there is in the blue mate choice side on the left, you can see there's 1, 2, 3, 4, 5 outliers, which have very many more jacks coming back than in general, versus the random male has only 1 outlier. I told you last time I reported to you that I hope that I could also report for the adults coming back, and actually we've done a lot of work on them. We developed libraries for them and deliver them to the sequencing lab, but unfortunately delay there has meant I don't have results for the adults that came back in November this year. I'm hoping that's going to come mature in the next few weeks, and I will email you guys about the adults. Sorry to disappoint you.
Sorry.
That's why you're here.
I tried to get her on time just to hear that.
I'm so sorry. It's really unfortunate. There was a miscommunication about a vacation time at the sequencing lab, and although we delivered them in time, they weren't put on the sequencer in time for me to be able to present.
So you hope to have something soon?
Very soon, yeah.
Is that something you can send out to the board?
I will.
Get it?
Absolutely. Yeah.
Prior to our next meeting?
Sure, I will.
Give me something to look forward to every day, because right now I don't have much.
Well, I hope it doesn't disappoint you. But we'll just have to see what it says.
All the assays went to serving the pandemic for a long time.
Yeah.
That's right. All the labs went.
So in terms of management recommendations, as I indicated earlier in the discussion, we are still completing our triple year design, and actually 2/3 of the fish are still out living their lives, and I don't even have the results from the 2019 adults. But if the jack results prove an accurate forecast of forthcoming results, then absolutely, wildlife breeding strategies and production hatcheries could greatly increase hatchery contributions to marine and inland fisheries, and even potentially may raise the fitness of hatchery fish to an extent that they're no longer a risk to wild populations. So it may in fact liberate hatcheries to be able to release a lot more fish. So I think it's very exciting, and I think it's very appropriate right now to start talking to all the different stakeholders, because there's a lot of different opinions about all these subjects, and it would be good to share out to them now. So I have 4 more slides just about the fin snipper, because the fin snipper is advanced a little bit, but I've already used a lot of time. Do you want me to just
Probably should just take 1 or 2 questions and then move on to the other presenters.
Can I just flip to the last one?
Yeah,
and
sure.
show
Yeah.
you the actual last prototype? So on the right there is a coded wire tag reader, and our machine is hopefully going to replace that. And here you can see it automatically fin snipping this top was from the 2000. And there's the fin clip taken. Sorry to have taken so much time.
No, that's great.
I have a lot to tell.
I'm just going to point out that when Michael started this study, and we were concerned with the practicality of actually applying it in the hatchery and the difficulty of getting the sample in a timely manner where you could actually use it. Then that led on to developing this machine that facilitate doing that quickly. Looks like that's coming right along. Right?
Yeah, it's not, well, it works, but not as efficiently as we need to sample 2,500 in a 3,500 a day. We had to use our backs, but we're on to prototype 3 now with metal that hopefully is more efficient.
That's coming out of the machine shop down at Newport.
Yes,
That is a nice lab.
yeah,
We gotta go tour that.
yes.
And the center is providing some monies for that, or did you get outside?
I'm getting outside. You guys gave me 50,000, and I also got 2 different grants from Oregon State. They have a business development program called OHRC Advantage, and they co-funded. They are co-funding this, as well as the Innovation Lab has pitched in some funds as well. And I'm also writing a proposal to NSF for that. And NOAA has just come out with a whole lot of Immigration Reduction Act funds, including for innovation. And I'm going to try and put my hat in for some of that too.
It's really interesting. Were you able to track at all survivorship in the hatchery between the two mating strategies? In other words, is there a difference in egg mortality or a difference in ability to start feeding, or where does the difference really happen? Is it once the fish are released from the hatchery, or did it go all the way through?
Yeah, no, we didn't. Unfortunately, there are very many more of them surviving at that time. So, it would be very costly to assay them at that point. We actually barely have enough funds to assay all the adult returns. So it's, it was something we originally wanted to do.
Because that is, if it's happening in the hatchery, then maybe you could do something about the hatchery.
Yeah, sure, absolutely.
And was there a large difference in egg numbers per female?
Just trying to remember.
Like when you're dealing with the alpha males,
Yeah.
Is it possible there could be 3 times as many eggs from the females that are involved?
Well, there certainly was variance. I mean, they were really large females that had a lot more eggs than the smaller ones. But I kept a really close eye on Charles, and sometimes actually I was the one that divided the eggs, and we needed to be very sure that we gave each beak an even hand. So I don't think that's a confounding issue.
Yeah, I wasn't thinking confounding here. What I was thinking is the possibility that certain genotypes also produce more eggs. So they can be more fit.
Yeah. We might be able to look at that anyway.
Michael, because we're focused on management recommendations, I think it's really neat, our script and the program that you developed, because I think a lot of hatchery managers would say we're already super busy and how are we going to work this into our workflow. But can you just describe briefly like what your experience was that, like adding that workflow to
yes,
the
that
production
brings to
schedule?
mind a refreshing memory, because we've been learning and developing tools along the way. And in 2019, at the very first spawn, we didn't have that program at all. We had Heather and Michael and our 2 computers. And sometimes it would take us 5 minutes or so to come up with the best male. And then we realized this is really not going to work, and we really need to get a computer to help us do this a lot more efficiently. So we went back the next year with our first prototype of that R program, and I was amazed. It always gave us an answer for all 10 fish, all 10 females on the rack within a minute, and we would just start calling out the numbers, and Charles is going, Michael, we can't work that fast. Why aren't you still spending all that time finding your chosen male? So it was really, really refreshing. Yeah.
If you go back 2 weeks after you've done genotyping and spawn the fish,
Yes.
is there a difference in maturity of the fish at that time? In other words, it seems like in most hatcheries, people would sort their fish and then sort of palpate, say, okay, this fish is ready to spawn. But if you're spawning everybody on the same date, you have certain females that are not as ripe as others.
Well, I believe that Ryan and his colleagues, when they choose, excuse me, when they choose the 500 fish to reserve as broodstock, they make that assessment. And in fact, one year we went and we genotyped all the fish, and we came back 2 weeks later, and unfortunately, we couldn't do the complete spawn because about half of the eggs were still green. And so we actually had to get more females, and we barely got our full experiment to happen that year. I think we got 110 families. We were hoping for 120 each year because of that. So that's an issue.
Yeah, what I was wondering is, and I don't know enough about coho, but in the wild, Chinook salmon, for example, spawn multiple times. A female will spawn multiple times. You know, the skein is maturing, you know, from the front back.
Sure.
So the eggs that are spawned are, the female knows that they're ripe eggs. But when you spawn them in a hatchery, you spawn everything at once. So you're spawning both, you know, those that are fully ripe, and then potentially a certain percentage of those that aren't quite as ripe.
Sure. Well, so I think this whole protocol will be much easier to apply to springline, for example, because you can genotype them much earlier than they return, and have a lot more time to get all your acts together, all your information together before spawning time. But, yeah.
For the sake of time, I think we can take Steve's question and then we'll move on to Mike.
Hopefully this is a short answer, but alpha male, that's just based on your genetic analysis as far as.
No, just based on how many offspring that male had returning.
Oh, you defined it after the fact.
I did find it,
Okay,
yes.
okay.
Yes.
Thank you, Mike.
What's that?
I think I'll have to click through.
Perfect.
All right. We'll stand up here so I can point. So like Michael said, the actual inception of the OHRC was largely motivated by this observation that there's huge fitness differences between hatchery and wild salmon, and the impacts on management are, of course, that then you have to hold back releasing your hatchery fish. So that's what we're trying to solve. And there's a lot of pedigree data from years ago suggesting that what's going on is very rapid adaptation to the hatchery. And you can see the effects within a single generation. So it's very quick. And so what our work has been focused on is what might you be able to change about the hatchery to reduce the rate of domestication selection so that your fish don't adapt to the hatchery as fast as apparently happens under normal conditions. And so that's what we've been exploring for the last number of years. And the premise of our work is this observation that when you release hatchery smolts, the probability of coming back, the probability of survival at sea is kind of this shaped function of the size at release. And so what we know is that there's a huge variation among families in the average size at release. So here's just some hypothetical made up data. So families 9 and 10, they on average were pretty big when they were released. Families 1 and 2 were pretty small. The way I've drawn this, most of your returns are going to be from these families, and very few of these would come back. So there's your selection. Now what's under selection is whatever it is that makes these families do well in a hatchery, their behavior, their physiology, whatever random deck of, whatever hand of genes they got from the deck made these families do well. There's your selection. But on the other hand, they come back overrepresented, and if they spawn in the wild, they're passing those genes on to the offspring. And we also have data suggesting that their offspring don't survive well in the wild. So there's your trade-off, there's your fitness loss. So what can you do about this? Well, the hatchery environment is so wildly different than the natural environment. We what we'd like to be able to do is if you could do something, change something about the hatchery so that you reduce that variation in differences in size among your families, then even if they're all smaller and you get fewer returns on overall, you've reduced the opportunity for selection. So if what you really care about is reducing domestication selection, then you'd like to be able to achieve this. So again, what's different about these guys? We have data suggesting that, and including from the literature, that one of the things that varies tremendously among families and is highly heritable is behaviors like generalized boldness. Some fish just seem to thrive in a hatchery, others are very shy and might do well. So what we've mainly experimented with is things you could change about the hatchery that are within the realm of could possibly be done. That would change things so that you would manage these guys relative to these guys, assuming that the difference, what's holding these back is like, say, they're excessively shy, for example. And so we've done a number of studies, and the last set, we're just starting to get some preliminary data, so I'm going to tell you about that. And these studies are basically Mimi's master's thesis. And in this study, what we've tried is 3 modifications to the hatchery. One is making the fish swim like you'd have in a recirculating aquaculture system. And the logic there is that in these types of systems where you make the fish swim at about 1.5 body lengths per second, is they tend to school rather than set up these diffuse little territories. You get better fin condition. There seems to be less aggressive interactions. The food disperses very quickly in the water. So the hypothesis would be, if in the scenario where you have these, shyer and bolder phenotypes, that everybody schooling like this is going to favor the shyer phenotypes. They're going to eat more and grow more normally. The other experiment was to add structure to the tanks. And here the idea is, instead of being in this big, barren, empty tank, which is standard practice, we give them places to hide. And presumably the shyer phenotypes, they're going to feel more comfortable, would maybe feed a little more readily, and perhaps even out the growth differences. And then the final is, because we have tried other things in addition to these, and none have seemed to have the desired effect, is we just went to just brute force grading the fish. Halfway through the growth, we divided them into small, medium, and large, and grew them separately. And what we tried to do was take the little ones and just put them in trout nirvana, super low density, high food, just everything to get them to catch up. And the big ones, we held them back. We fed them less, tried to basically have our 2 targets converging on some middle optimum. This is also an interesting study because it gave us the opportunity to test one of the premises of our work, and that is that the little ones are doing poorly because they're being repressed by the big ones. Alternately, the alternate hypothesis is that they're just physiologically or behaviorally unable to do well in a hatchery environment, regardless of the presence of fish, they're doing better. So by separating out the little ones, we get to test, okay, if you remove the big dominant ones, do they catch up? So that we've allowed to do that for this study. So the flow experiment this was done at the OHRC in the 6-foot tanks. Like all these experiments, we created a bunch of full sieve families, pulled them together in equal numbers and put them in the tanks and replicate tanks. And we used a stand pipe to make the water swirl at a desired rate. This is work we did in collaboration with Jen and Craig Lawson, who was here. And so basically, ran them for the length of the experiment. We had 4 control tanks, which were the standard way with a stand pipe in the middle of water kind of cooling out. And then 4 treatment tanks were the flow tanks. And so at the end of the experiment, we measured the length, the weight, the condition factor, which is basically a measure of how fat they are. And more importantly, the coefficient of variation for each of those traits, which is a measure of just the variation among individuals. Now we're still genotyping all these fish to sort them back into families. So at this point, we don't know what the variation among families is, which is what we're really interested in. But it tends to correlate with just the total variance. So I'll talk about that for now. And basically what we found is with this experiment, interestingly, the fish were slightly larger in the flow tanks, even though they were being fed on the same schedule to all get to six pounds, what is it, 6 fish per pound. But we saw there was a minimal effect on the overall coefficient of variation. Again, the family effect, we don't know. So what this is showing here is, this is the average length of fish from each tank. These are the 4 control tanks. These are the 4 tanks that had flow. So we see a slight main effect, although that isn't really what we were interested in. We were interested in the variance. This is the coefficient of variation in the length of the tanks. You know, if you squint real hard, you might say, well, it's slightly lower in some of the structured tanks, but not enough to be significant and interesting. Oh, I labeled these structures. Sorry, I think I got the wrong one. These are the flow ones. All right, so for the structure experiment, this was done at the Aquatic Animal Health Lab over by campus. Again, we had 4 control tanks, 4 treatment tanks. In this facility, we're using 3-foot tanks, and we put these little structures in here, which were designed by other researchers at the OHRC. I think Carl Greavy came up with these, right? So again, the idea is that the Shire fish, they've got a place to hide. There's going to be, you know, less opportunity for bullying, more ready feeding. And so here, again, minimally larger in the structure tanks, which is kind of interesting. But what we really cared about was the coefficient of variation, and we see that there's no average effect. Again, we don't know what the family effect is, but unless it's going to have a huge effect on the among family variance, my guess is neither of these experiments is going to show what we had hoped for, that the among family variance has been appreciably reduced. So let's talk about the grading study. So this one was actually turned out to be the most interesting. We started with 4 tanks, 2 control tanks, 2 which we were going to do grading on. Halfway through the experiment, each of these tanks we divided into 3 tanks, small, medium, large. Basically, we took the bottom 25%, the middle 50%, and the top 25%. And the idea here is we want to know at the end of the experiment, just as a whole group, all of the graded fish, if they were all released together, what does the variance in size and does that distribution look like relative to if you took all the control fish and released them? So the way we did this was we actually took the 2 large groups and we pulled them together. And the reason here was we wanted them to have less ideal conditions. So they're higher density and we fed them less. Then we had 2 smalls, which, like I said, were trout nirvana, super low density, gave them plenty of food. And then the mediums were kind of kept on the same trajectory as the control tanks. So again, we set it up in June, took it down about 5 months later. Didn't take it down. We did the grading in 5 months later, and then ended the experiment in April. The smalls, we had the target of 5 fish per pound in our feeding. The mediums and the controls at the standard 6. And then the larges, we were trying to hold them back, so our feeding target was 7 fish per pound. And here's what we got. So I'm going to walk you through this figure. So this is the average length of each group. And when we set the thing up, these are our small, medium, and largest. So when we set it up, we had big differences initially. This was if you pooled all the graded fish together, and this would be the controls. All right. And this is at the end of the experiment. And what you can see here is the little ones never caught up. The mediums and the largest, we held them back. They're even slightly smaller than the medium. So we very successfully held back the big ones. The little ones never caught up. And so basically we have these groups here all lining up about the same. So this is really quite interesting. And if you actually look at the distributions, this is, for example, length, which I've just been showing in the previous graphs, just to keep it simple. This is the distribution of length among the controls. We always see this really strong left-hand skew. There's a lot of fish that are just small. And this is after getting rid of the ones that were obviously deformed. But there's always a very strong left-hand tail on these distributions. And you don't really successfully pull it in with what we tried. Now, what you can see is we definitely lopped off the right-hand skew where you typically have a lot of very large fish. We pulled that back. And in fact, the total variance in this group is statistically significantly higher than the total variance in this group. And I'll show you the weight data too, because it's a little more striking. You can see the same pattern. We didn't really pull in the left-hand tail, but we definitely pulled in the right-hand tail. And again, statistically significant differences in the overall variance. It'll be really interesting when we finish genotyping them into families, but based on past experience, I can almost guarantee that these guys are one set of families and these guys are another set of families over here. But we're still doing all the genotyping. So, the family effects, like I said, we're still working on that. All right, so conclusions and recommendations. All right. So we've been doing this for a while now. We've done a lot of different experiments. We've tried, flowing water and structure. We've tried using tenfold reduced densities. We've tried automated feeders versus hand feeding. We tried satiation feeding versus, normal, giving them the same amount every day. We even tried low fat versus high fat treatment. And we also had 2 years in which our experiments were wiped out by disease. So we actually have been doing something. But my conclusion so far is unless the genotyping data tells us something different, that these simple manipulations to the hatchery environment seem unlikely to appreciably reduce the variance in size and in particular the among family variance. So basically with these type of kind of simple manipulations, you can't overcome the family effect. It's probably still going to be there. You'd have to be much more aggressive. And now we're out of the realm of things that could reasonably be done in a hatchery. Now, the brute force grading could partially work. Clearly, you can hold big ones back. So there might still be some scope for trying this at a production scale if one really wanted to keep pursuing this line of research. But again, I think the result of all this work is this family effect, the genetic variation in predisposition to either doing well or poorly under hatchery conditions is just too hard to overcome, which is kind of disappointing for me because I thought this would work. But we set out, back however many years ago, 6 years ago, to answer a question, and I think this is the answer, which is disappointing, but it is what it is. So, can you reduce domestication and still have a hatchery? So you could keep being more and more aggressive. You could do flowing water and structure and, gravel in the bottom. Eventually you're raising in an artificial stream and you have lost what a hatchery gives you is the production numbers. So I'm starting to come to the conclusion that, if you really want to reduce domestication, this rapid adaptation to a hatchery, you would have to change things so drastically that it's not really a hatchery anymore. That's where I think we're coming down on this. Which means that, okay, so you still got this problem of fish that rapidly adapt to captivity. They go out to sea and come back and they're spawning with your wild fish. That problem hasn't gone away. We know it's still there and we know the effect is large. And your two options were keep them apart or reduce the rate of domestication. I'm starting to think that maybe all the energy needs to be on keeping them apart, doing stuff like the olfaction study, basically mitigating the mixing on the spawning grounds. So, so I think that's where this is all going to land. Again, I'm real curious about the genotyping data and sorting them back into families. And I think, like I said, there's still potentially some scope for looking at the effect of grading. One could do an experiment where you do grading at a hatchery level, at a production scale, release them, come back and see if in fact the variation among families, the number of survivors per family, if that variation has been reduced, that might be worth doing. But other than that, I think these simple things that one could easily do in a hatchery without driving the hatchery managers crazy are not going to work. So there you go. Questions?
So yeah, are you essentially done with this research?
I think so, yeah. I don't think trying other manipulations of this type is is worth doing. Again, what we set out to do 6 years ago was we're going to do a series of these short-term experiments. Each of these experiments takes like a year and a half. I think we've done enough. We've tried all the things that people have reasonably tried in hatcheries for increased production, like, nature's way stuff. It's like, I'm not going to suggest you throw a bunch of Christmas trees in your raceways. I don't think it would have the desired effect. So yeah, I think this line of research has answered the question we set out to ask. Yeah.
If you are assigning this then variance that hatchery management might not be able to overcome as a familial traits or genetic traits, have you any hypothesis or thoughts around what those traits would be? Is it you're just set to grow to a certain size, or is it that you are able to better or not as well take advantage of nutrients in the system? Like what aspect of a genetic component is contributing to this seemingly varying to size?
Yeah. So, what is it that makes that first slide back there? Yeah. What makes these guys winners and these guys losers? It's either behavior or physiology, ability, like you said, to process food. In nature, your little fish pops up out of the gravel. It's got to establish a territory. There's predators. There's not an abundance of food, and it's high protein, low fat. So there's certainly scope for physiological adaptation. These guys might just be able to process unlimited quantities of high fat food better than these guys. That was the logic behind our high fat, low fat experiment, which did not have the desired effect. I still believe that behavior is a huge part of it. I still think that just generalized boldness is under strong selection at hatcheries. I think these ones, it's really interesting. When I first started this work, working out with the Hood River stock at the hatchery out there in the Deschutes River, I remember the hatchery manager, Lyle, he takes me out there and shows me, these two tanks. One has the old domesticated stock that they had at the time, and the other was the F1 stock. And these guys over here, they just, they're just kind of swimming around, looking up at us. And these, you leaned over and they're all darting and hiding in the corners, and it was just stark. And if you go like to any hatchery and you look when they first put these little fish in a Canadian trough, it's like some of them, they're kind of milling around at the top, and others are hiding in the corner. And those ones don't thrive. And I'm pretty sure, and also, we see huge variation among families and propensity to feed at the surface versus not. So I think that's a huge part of it. We tailored most of our manipulations on that assumption, things like structure and flow and how we feed them, that sort of thing. So, if we're completely wrong on that, then maybe there were other manipulations one could have done that would have the desired effect, maybe focusing more on physiology. We didn't go down that road as much, so maybe there's scope to do work on that. I think it's largely behavior, and I think it's going to be really hard to overcome. So, sorry, that was a long-winded answer to your question. Did I answer it? All right.
The one thing is still, you mentioned the F1s were more wildlife with their, but still you put them in, they come back after that one generation and have a 50% hit in survival. That still amazes me that it happens so rapidly.
It's their offspring that have the 50% hit in survival. Your hatchery fish, it's the survivors that come back. Obviously they made it back, but it's their offspring who don't return. So
right, but still it's just that one F1 in the hatchery.
Exactly. Yeah, it's stunning. And this has been shown again and again and again. There's like, a stack of pedigree-based studies showing that hatchery fish produce fewer surviving offspring than wild fish. And we were the first and got a lot of flack for it, but now there's like, 12, 15 studies all showing the same thing. So it's kind of it's a thing. So, yeah.
I think you're totally right, Michael, that it's both behavior and physiology. Back in places currently, and I did some studies with coho. We found that if you're truly subordinate, you can't perform well, even if you remove any other behavioral effects. You don't feed as well, you don't grow as well. I'm guessing streams usually ones that perish.
Well, interestingly, so we did a previous experiment where we actually compared F1 hatchery, the offspring of F1 hatchery fish versus the offspring of wild fish. And as expected, the offspring of the hatchery fish grew faster in the hatchery, but when we put them in the artificial streams, they had lower survival. Boom, there you go. So whatever it is about these guys, they're favored in the wild. So that's, first of all, that's why you have all this genetic variance. The wild is not a static environment. So these guys, that's your trade-off, is these genotypes, they probably do better in the wild than these genotypes. These guys do better in the hatchery, and then you've got this trade-off. You can't be good at both at the same time. So that's gonna be really difficult to overcome, I think.
So we had a meeting last week with ODF&W and also talked with Carl in the car on the way up here about bird predation. And seems like these full fish are probably likely making themselves into snacks, basically.
Exactly, yeah. They come back, they pass those genes on to their offspring, and you never see them again.
So how do they persist over generations if they have that selective pressure?
Because, so that's basically, you're asking a basic question, is why is there heritable variation in nature for anything? It's because the natural environment is not static. It's probably constantly changing, and your optimum phenotype in 1 year is different from
Right, so
the previous year.
So some years that could be an advantage.
Perhaps, yeah. So basically, whatever the traits are to make these guys winners and these guys losers are highly heritable, and just adapt really quickly. That's why I still like kind of generalized boldness. It tends to be highly heritable in pretty much every creature anybody's ever looked at. And it totally explains a lot of what we see here. Plus, there's other literature showing, where people compare domesticated and non-domesticated stocks. The domesticated ones, they don't avoid predators, they come up and feed at the surface, just like all the things. So, yeah.
I've kind of noticed through the years, just all the fish caught commercially and returning to the rivers, they're becoming smaller and smaller. I don't know if we're finding that in real life, but it's just, a lot of the fish coming back into the Columbia this year are 7-8 pound fish. 20 years ago, they would have been 4 or 5 pound bigger. Is this hatchery effect of?
I don't think so. My guess is that probably has more to do with other things.
Habitat, feed, and
exactly. It's not like, growth is always good and fast growth is always favored. It's like, what traits do you use to get there? And the traits that allow you to grow fast in this environment probably help you grow fast in the wild, but they also get you eat them. So there's a trade-off. So what we're selecting for is fish that do great in a hatchery, but their offspring are, they're out foraging when they should be hiding. They're starving to death because metabolism's ramped up too high. All the things that make you do well in a hatchery probably cause a huge survival cost in the wild, which is why we see this fitness trade-off. That's what's going on. So I don't think we're selecting for necessarily faster growing. Well, certainly not. We're not selecting for less fast growing fish. So I don't think that would explain your observation. It's probably more ecological.
I think it maybe matters on how you grow the fish. I remember some stuff that Brian Beckman did that showed that a fish that's released, basically when it's growing fast, is better smolt than a fish that's released. These are wild fish, migrants, that have grown and stopped growing, and then wound up being during the smolting season. In other words, a hatchery, say, for example, that grows its fish up to size, then restricts them on feed, versus a hatchery that grows them and feeds them well at the time of release. But two different strategies, two different physiologies.
There's more things you could tinker with. Lots of things you could change about a hatchery. At least the obvious ones, I don't think they're going to work. So I personally don't want to keep doing this kind of work and keep having negative results. So I think there are things other people could pick up and run with. But yeah, you'd have to think it through. Yeah.
I live in Tillamook, and in 1997, we started using wild fish for food stuff. That was 26 years ago. And we have the best wild runs on the coast. We have the best hatch runs on the coast. Could something be being lost in the experiment design where you're doing it in artificial streams instead of real streams? And I know there, I got to see we have an acclimation pond. When they put the wild smolts in there, like you're talking about, it's like you walk over the pond and they go to the other end, and they're real wary. But it just seems like there's some disconnect between what you're saying and what that 26 years of experience is.
Well, certainly using first generation hatchery fish each time, constantly using raw brood stock is better than creating these really, multi-generation domesticated lines.
So, and those fish escape, some of them spawn in the wild, and wild run is still really fast. It's like, I don't know, it just seems odd.
All right, thank you. Thank you. Okay, while we're queuing up Dr. Dittman's study, we'll make a public service announcement that everybody at some point today, make sure you sign in on the sign-in sheet, and there is snacks over in the corner. So
And there's no break, so there's restrooms around the corner.
yeah, there's no official break written into the agenda, so the restroom is to the right.
I think I'm gonna do what Mike did and here in between things, so sorry if online people can't see any of that. And we did not pay Mike to say the emphasis on the factory imprinting project. Should I start? We're good? Yeah. So I'm up here representing actually a collective of very smarter than you people. This project started sort of at the same time these other long-term projects began. David as our leader. Subsequently, since Seth has joined, he's joined our group, and it's been a wonderful addition, giving us new ideas. Mark Johnson with ODF&W has been involved. Tom Quinn has sort of peripherally been involved for a long time, is now formally part of the team. So it's really a nice group of folks. I'm probably going to emphasize only a few little areas. I feel like there are a lot of key findings, because this has been a long-term study. There are a lot of key findings, and the emphasis on recommendations. I'm sort of just going to focus on a few aspects of the work we've done, but I'll happy to come back and give you a 2-hour-long lecture on it. So we were asked to provide some background and context for the work. Our project, sort of the overarching goal of our project was a particular hatchery situation, the Elk River Hatchery in Southern Oregon. But straying by salmon, hatchery salmon in particular, is a major problem wherever salmon are reared in hatcheries. Some hatcheries are not inherently a problem. There are hatcheries where you have extraordinary homing fidelity, but some of the things we do in hatcheries can create problems interacting, particularly fish spawning in the wild and interacting either ecologically or genetically with wild fish. And so the genesis of this project came part of the ODF&W's Coastal Management Conservation Management Plan back in 2014. They identified populations of coastal salmon that seemed to be in jeopardy, and one of those was is this a laser pointer? One of these was the Elk River Hatchery, where there was a real concern about the wild population, because the hatchery population, a large percentage of those fish, in some years back a ways ago, 50% of the Chinook salmon spawning in the Elk River were hatchery fish. Nearby Sixes River, 30% of the Chinook salmon spawning in the Sixes were hatchery fish. And so there's real concern about the wild population. And so that led to a recommendation in reducing the hatchery production, so fewer opportunities for fishing, which didn't make people happy. And so they did reduce that, but they also reached out to the OHRC and asked them to get involved and perhaps recommend strategies for trying to reduce the number of stray fish spawning in the wild. And so that was the genesis of our project, and we sort of discussed various aspects of this and tried to develop objectives that we could explore of whether we could improve the homing fidelity back to the hatchery. One of the primary ones that I'll probably spend most of the time in is trying to develop methods to attract these hatchery fish back into the Elk River hatchery by adding a unique chemical signature to the hatchery to create a distinct odor signature that salmon can imprint on and then follow back to the hatchery when they were adults. We've also been working on some other aspects of this. One of them is and I'll talk more about this in a minute, but there's some suggestion that exposure to surface water, natural waters versus well water, which are used frequently in hatcheries for incubation because it allows you, for one, well water is typically pathogen free, which is important, and it is fairly constant temperature and typically warmer, so it allows hatchery managers to manipulate the developmental processes in the hatchery and get fish to the size they want or ponded at certain times. It just allows a lot more control in a hatchery. And then finally, not only is it important what the odors are they're learning and what waters exactly, but these fish are imprinting in developmentally sensitive windows and understanding each species, but also in fact, each population may have distinct imprinting windows where they're especially prone to learn these odors prior to release into the environment. And so we know that if you release a fish too early or too late from a hatchery, you actually can see increased stray rates. And so those are sort of the major objectives we're tackling. The first several years is a flow chart based on flow chart sites. But anyway, sort of listing the different phases of the project. And the first phase of the project was trying to identify odorants that might make sense to add to a river to give them a unique signature, and I'll talk a little bit about that. We're interested in then actually exposing these fish and testing for tools to tell us when fish are imprinting and what odors they're imprinting to. And then we're in this phase now where we are actually doing a hatchery scale experiment, quite similar to Michael's mate choice study, where we have 3 brood years of fish released into the environment that have been exposed to imprinting odors, and then we're drifting those odors back to the hatchery to see if we can improve their homing. So we're not going to read this, but one of the things that Seth sent out said, you know, we want to really tie this. How does your work relate to the OHRC's mission? And so I actually clicked on the link, and in every way, in my very biased opinion. And so this is just showing you many of the things or the highlighted things, and I'm not going to read it, but you know, we are, I think, trying to do many of the things the OHRC's mission suggests we should. And so here's even more. We'll go into that. So key findings. The other aspect of these talks, we were asked to give sort of key findings and what might be the management implications of that. And there's a lot going on this slide. We don't have to get into the details, but basically a lot of the initial work, as I said, has been evaluating the potential imprinting odors. So odors, salmon, as you know, learn odors in their natural streams before they go out to sea. When they come back, they use those odor cues to find their way back. There's a concern in some hatcheries that when you're using river water directly taken from the river into the hatchery and back out into the river, it might not be creating enough of a unique olfactory signature in the hatchery that allows fish to distinguish the hatchery from the river as their home. So the idea is, can we identify odors that make sense that salmon we know can smell, can learn, will use as imprinting cues, and are not dangerous to the environment, etc. So we did a whole series of behavioral experiments where we looked to see if fish had an innate attraction or avoidance to odors using wine mazes. We did physiological assessments of whether they could smell different odors. We did conditioning experiments looking to see if they were able to learn those odors, and we've developed a whole series of markers that we are hoping to use to identify when a fish has imprinted these odors. So early work is focused on discrete specific odors and led us to our experiment using discrete amino acids, a cocktail of these 3 amino acids. We are now actually in this new phase of studies. We are actually looking at sort of more complex odors, both motivation there being both maybe giving a fuller olfactory signature, but also maybe provide cheaper, easier to use odorants. And in fact, some of you may have seen there was an article in the Oregonian about potentially using byproducts of beer as one of these odors that we might use for him. So, as I said, the other aspect of this was management recommendations. I don't know that there is really specifically a management recommendation associated with this. Key findings is we have identified imprinting odors, and we're finding new odor, complex odors that will be useful, we believe. But basically, we've developed the tools for testing these different management applications. And so we're doing those experiments right now with some of these initial odors, and hopefully in the future in Elk River or other hatcheries where it makes sense, using some of these other more complex odors. And this, these are the criteria Seth gave me. So here you go. I think the odors, we have a high confidence level. These odors can work. We know these fish can use these. Not sure there's a timeline per se, other than once these experiments are done, then we can implement them and incorporate them into either new studies or actual management recommendations. All right. One that we have not emphasized as much in a lot of these discussions, but we actually are nearing the point where we have all of the data, is trying to understand the importance, as I mentioned, that there's a lot of hatcheries that use well water, but there is a suggestion that salmon develop differently in well water versus natural river water. So what's different about well water versus river water? Well, first of all, and when we get to the management implications, you'll see there is no generic well water and river water. That's one of the things that I think is important in all of these conversations. But we've done a number of studies. In fact, my earliest interactions with David were actually looking at embryonic exposure of fish, steelhead and spring snook here at the OHRC, and just looking to see if we could condition fish to be attracted to those odors. So hopefully imprinting. But what we learned, and so this is percentage of fish, OHRC, fish attracted to OHRC Fall Creek water versus well water. So this goes from, I think this starts at 50%. So essentially all of the fish that were incubated in Fall Creek water right here at OHRC were attracted to OHRC water. But the fish that were incubated in well water, which we had assumed, okay, now they'll learn that as their home, they'll be attracted to that. Well, no, only 20%, 80% of them were attracted to the stream water, only 20% were attracted to the well water. So we could shift this both in steelhead and spring snook. But there's something innately about the well water that they just didn't like. And so there could be lots of reasons. It could be toxins, there could be other things going on, and different wells are different. But the other thing we've learned over the years, my background has been in trying to understand the physiology of olfaction and the sort of the odor receptors involved in identifying odors in the environment and then signaling to the brain that there's an odor. And so this is one particular odor receptor that we believe is activated by amino acids. This is looking at the development of that, the expression of that receptor over time. Fish reared either in well water or big beef. This hatchery up in Washington. So either the stream water or the well water, and we were just stunned. We really didn't expect this result. You see the sort of normal smolting associated increase in expression of this receptor in stream water, but almost nothing in well water. So we were surprised by that, and we were wondering, well, so why? What's going on? And one of the things we found, just looking at amino acid concentration, these are a list of amino acids, this is the concentration. Basically, the river water, the creek water, has this huge complexity of amino acids, and the well water is essentially none. And so we don't know this, but perhaps that complexity is important for the normal development of the olfactory system. And in fact, we know from other studies that fish reared in more simple or complex environments, whether the stream, the hatchery, or typically will have differences in their brain sizes. So fish reared in the river will have larger areas of the brain that are involved in olfaction and spatial orientation versus the simple environment in the hatchery. So there could be things going on with these differences in complexity of the water. That led us to be concerned that maybe this is a factor in homing. So is river water important for fish to home successfully. And so we actually were given the opportunity, like Brent, others allowed us to do this experiment sort of early on. We were identifying other imprinting odors where we exposed Elk River fish to either well water or river water as embryos. Each group was reared separately. They were tagged and released. The fish that came back were either recovered at the hatchery or in the spawning grounds, and we tested for treatment effects. We were able to do this for 2 years. The fish, it was brood year 27, 2018. We're waiting on this last year, but most of the fish are back now. And so all of this is preliminary, but I think we have enough data to kind of say, make some conclusions, although they're not the final. And the bottom line is fish reared in river water versus well water, the traditional way. What you see is 6%, 6.6% of the river water fish strayed, 4.85% strayed the well water fish. The survival of the fish were not great, but similar. And the bottom line is, again, this is not the final data, so there's no statistics here, but if you look at these numbers, the brood year 2017, it's around 5-6%. Year 2018, it's around 4%. Survivals aren't that different. It doesn't look like you're going to really shift things dramatically either way by rearing the embryos in river water versus well water. And that probably makes lots of hatchery managers happy, because I've been trying to do these kinds of experiments for a long time, and they all don't like me bringing river water onto their embryos and making them all sick. So again, here, river water key findings: embryo exposure to river water with well water did not seem to impact the olfactory development, which is data I didn't show, but the whole series of physiological assessments also didn't really show any differences, or the homing success. So I guess, and again, I will caveat this: we have a great team of very smart people, and convergence of internet failures and our schedules, they haven't all weighed in on this. So this is what I wrote, but as part of the board and the rest of the PIs on this, we probably could develop better recommendations. But so embryo rearing in well water is an effective strategy for disease control and regulation of development, and in some hatcheries does not affect homing success. And because scientists, I always have to caveat it, some hatcheries. Well waters differ between hatcheries, and each hatchery's well water should be examined for potential deleterious effects. So I think in the Elk River, well water, there are some wells that are quite deep, very different water. This one has a bacterial load. I think it had flocculent associated with bacteria when we were doing it. Well water at the Elk River is, it's called well water, but in fact, it's probably just hyporheic water. It's a pretty shallow well, so it may just be really river water as well. And that may be why we didn't see those effects. So I think we have to keep this in mind when we make these recommendations. That's my confidence levels are medium, I guess. And we're still collecting the data, but soon we'll be able to make some kind of final recommendation. All right, and then sort of the big experiment, which is adding odors to the hatchery water, trying to improve homing. That's similar to Michael's. We're honestly, we're waiting for the results. I'm not going to give you any gee whiz results or recommendation, but I'll catch up to date on where we're at. So in this experiment, we exposed juvenile fall chinook to these amino acid cocktails of odors, either as embryos or as smolts, or we had a controlled treatment. The fish were reared and tagged by raceway and by treatment. As fish are coming back, we're collecting the tags, exactly the same as the river water, well water experiment. Collect the tags from the spawning grounds, the creel, the fishery, and the hatchery. So this was conducted 2019, brood year 2019 through 21. All of our fish, so all of these are the same, but so we have 3 raceways, 90,000 fish exposed to amino acids as embryos, 90,000 exposed as smolts, and another 90 as just controlled river water, which were released, and then we collected adults as they come back. And so you can see we are beginning to get returns, but we really have essentially no data except for the JACs at this point, because we don't have the code wire tag data for 2022. And so we're looking at really 2026 as the year we'll have all the data, all the fish collected, again, there's a lag with COVAR tags, so realistically, we're probably, looking at 2027 and get all this back. So this is just, I guess that's sort of some of the stuff I just said. This is showing you some of the odor exposure methodology and dripping it into the hatchery, the return water, and this is just showing you it's all ongoing. So, recommendations, the key effects of imprinting odor in additions to improve hatchery salmon really are not known yet. I can't really say anything about that. I think we can fairly confidently say, based on our previous work, efficacy of odors for imprinting and altering the river and hatchery chemical signatures. We've established, though I didn't talk about that at all, I'd be happy to, about all the chemistry we did, looking at the river itself and how it changed with our odor additions. Develop these delivery systems that could be used in Workendale River, could be used in other hatcheries. And so, again, cannot provide overall management recommendations, but the criteria for which hatchery programs may benefit from these practices have been developed and are exportable. I'll talk about that in a minute. Confidence level really, these we're just waiting. There are other key findings associated with, just sort of the demographics of fish that stray, the migratory behavior with radiotelemetry study. These are published. Done a fair bit of work looking at the appropriate timing of exposure that we've used, and developing tools to assess what's in the river, what we might add to the hatchery to change those signatures. I don't have recommendations for those, but all of these will go into those recommendations ultimately. And so this is sort of as our part of our new proposal, and specifically as Seth has come on board, we're thinking more and more about how hatcheries are used, particularly in the face of climate change. There's a lot of things that hatcheries are going to have to change as they go along because of changes in flow and temperature. All of those might affect imprinting and homing. And so many of the toolkit we're developing and the approaches, I think, can be applied to very specific hatcheries programs throughout the state in the future. And so we're meeting with hatchery managers to kind of start thinking about how these techniques might work in their individual situations. I think that's it. Yeah. So, questions?
Can you share with us the results of the jacks in 1 year?
Well, honestly, there's so few. I mean, there was no obvious difference, but there was so few, and the problem is they get very few jacks on the spawning grounds. So we really have no, we know what came back to the hatchery, and there was no obvious numerical differences, even though it's not a big number. But spawning grounds, I think there were none covered. And that's typical.
Was there many 3-year-olds? Hope there's some, I think.
Yeah, they're. I always get you confused. I've worked there for years, and now my year class issues are. So the 3-year-old, the 2-year-olds are down. Yeah, so there are. I think the 3s and 4s are the major ones. So we have that 3-year-old data, in the freezer. Someone may have all the data. We're just waiting on the code wire tag data. So again, if we get that, I can send that. We'll get that data and let you know, because it will be the first hint of that. But I don't know. Mark's not here. Mark's sort of Mark Johnson, our conduit to the tag lab.
So all our code wire tags have been read that were collected in 22 this last month. So they're in the system somewhere. If you need help with stuff.
Okay.
Mark was able to pull together that surface water, well water data really quickly. So
Yeah. He's sort of, he's kind of. Good, excellent, okay, great. So even sooner than. Yes.
I'm curious about, initially, you guys tested these amino acid complexes.
Right.
And now we're looking at other compounds before we have the results if the amino acids actually work or not. And that just curious to me as to why would be the timing of that.
Yeah.
Shouldn't we kind of be, or should we have not used amino acids in the first place, or what happened?
Yeah, what happened? Well, a couple things happened. So we know there's a lot of evidence. In fact, there's some suggestion. There's a Hiroshi Ueda in Japan that's published a lot on suggesting that amino acids may actually be sort of the key chemicals in river water that salmon use for imprinting. There's a lot of work and suggestion that bile acids or something associated with fish themselves, pheromones may play a role. There's data that minerals fish can imprint to. So we looked at all of those. We looked at the ability of fish, this olfactory sensitivity, the ability to learn these odors, all of that was put together. I usually probably, some of you have seen this giant spreadsheet, this table that shows all the criteria. And so amino acids were sort of selected at that time as the best likelihood to work. And so we made a decision to use highly pure amino acids, which I think was important because this is our one chance to test this theory. It's going to work. If this works, then we can expand it in many ways, both the odors and the hatcheries beyond that. So with the pandemic, supply became a major issue, inflation became a major issue, and these things are costly. So it became clear pretty early on that these pure amino acids were not going to be the solution for ODF and W if they have to pay tens of thousands of dollars every year to drip odors into the water, because you're dripping continuously, at least the way we're doing it, we're continuously dripping water into the ladder from November through January for sure, even maybe a little more than that. So it's expensive, and so there was internal debate because I've been an advocate for some of these more complex odors, thinking that they will provide a tank full of fish or beer. You're talking about hundreds of odors, not just 3 that we're adding. So I think it provides a little bit more of a unique signature potentially. It's probably cheaper, but it is less. I mean, the downside is there is variation in seasonal variation, a different batch of brew beer, all of that there's variation in that. So it's not going to be quite as consistent. And how much that matters for families, that we don't know. So there's trade-offs. We thought that, we're looking at 2026. If we wait till 2026 to say, oh, that didn't work, but what about these other odors? That's, then we're however many years behind the curve there. So we're trying to test these in advance. So all those, can they smell it? Can they learn it? Is it dangerous? Is it inexpensive? Questions we're trying to do now before we get the results from the amino acid.
So all that, I forget her name, but she did all those
Mary.
Y maze stuff.
Yeah.
You're doing that now with
so we've done that with
beer byproducts?
Yes, we've done those experiments, and in fact, in April, I lived here in April, so we did those experiments.
So the plan is to have more releases with the different.
Honestly, we haven't gotten to that point. I mean, we haven't gotten to that point, but I think ultimately, yes, I think we'll have potentially doing those kinds of things in the context of other hatchery programs where it makes sense, perhaps, but we haven't actually gotten to designing that experiment.
Seems like that we have to have something where we decide if it's going to work or not in the best case scenario.
Yeah. Well, 2026, we'll have that answer. Hopefully.
I might still be around.
Yeah, well, you and me both. Yeah.
But Steve, in our proposal that was approved by the board, this next phase of research includes developing physiological and genetic markers that are proxies for imprinting. We won't know until we actually, try it at a hatchery and release them. But like Andy said, if you just do the experiments back to back, each odor is going to take 8 to 10 years to figure out, and we just don't have that time.
So hopefully those translate to actual behavior down the, real use.
We encounter, I encounter almost on a daily basis people at hatcheries asking how to control for hatchery strays. So I think this is a really high interest, and we're going to be able to apply it. And the timing isn't always perfect, but we got to keep moving and trying these things out.
Yeah, that's well water, river water.
Yeah.
So it's really important.
Yeah.
It's good to You got that?
Yeah.
I was wondering about the experiments. And when they were basically YMA sorts of tests of hatchery versus well water.
Oh, yes, gotcha, yeah.
And you implied that there was something negative about the well water. They're avoiding it. And do we really know that,
or
is it
especially
possible that
attractive about the river water, yeah.
maybe river water just smells so much better, they liked it better.
Yeah, and yes, I guess I should not have phrased it that way. Yes. Although, like I say, we were sort of surprised that there was this innate preference that, learning could shift it, but it couldn't overcome it. Even though that was their home for, a month or two, they'd rather live in the stream. Yes.
Do you think that the well water versus river water preference is related to the compounds that are in the water, or something that is physiologically like development related in the fish? So like, are there developmental triggers for certain genes to be turned on and off in the fish versus the well water just innately smells better? I mean, river water.
Right. Well, that was it. So what's the answer? I've sort of operated under the assumption that it is the complexity of the water. And in this particular case, because this particular odor receptor that we were studying is a receptor for basic amino acids, so bar basic amino acids, etc. So arginine and lysine. And so what we found is exposure, this is going down a deep hole, but we found exposure to this amino acid actually alters the expression of this receptor. And so if you look here, this one's arginine right here. I think lysine, so that's interesting. Higher than I was. Oh no, this is natural river water, sorry. Whereas the well water, there's nothing. So we think maybe this is related to the fact that those amino acids are present and actually stimulating the expression of that receptor. So, but indeed, it is a different environment. There's probably different regulatory things going on. So all of that could impact the fish's physiology and behavior.
I'm obviously interested in it from a microbiome perspective.
Yeah. Well, and yeah, we've talked about that before. It would be, there's lots of really interesting things, the environment they're in and how that affects their.
I can't read that.
I'm sorry.
You have serine on there?
Yes, sir. Yeah. No, so you're wondering if they're avoiding serine?
Yeah.
This is serine. So that's the natural, that's the river water. And there is a little bit of serine in the well water, but it's not, well, you've done those experiments. We've tried to recreate some of those experiments up in streams in Alaska. And there's this suggestion that like mammalian skin releases serine. There's essentially, if you want a good source of amino acids, stick your finger in a glass of water, and it's just crazy. We use that for our controls for those physiology experiments, because it just goes off the roof, off the roof. So there's a suggestion that washes from mammals contain high levels of serine, which fish avoid, salmon avoid. And there's these experiments where they waved bear paws in a fish ladder and looked at the differences in migration and it's crazy stuff. But Carl and others have done a lot of experiments looking at serine as a salmon avoid serine innately. And sometimes we see that and sometimes we don't when we try to do those experiments. So. Yes,
We
sir.
probably have time for one more question. So.
Okay, sorry, I probably was way long. So.
You're doing great.
Did you use wort, the basic, when they at the material that had grain and those other objects in it, or did you use just a yeast with a sugar base and warm water?
I'm going to defer to Seth because he's our expert.
Seth, what do they do?
That was we used two different types of spent yeast. One that was brewed with hops and one that was brewed without hops. We thought maybe the hops would make the water too acidic, but actually when Andy extracted the odors, it turned out that it didn't affect the pH.
So the yeast didn't make any difference. So yeast is real easy to do that anywhere cheaply. Basically sugar, water, warm water, and grow it.
Okay, yeah. So we just used the straight spent yeast in a hops versus no hops batch, and then we used the spent grain of another batch before it had gone
That was slightly less. Seth actually gave a really nice presentation for the meeting. Spain, but on sort of that aspect, some of that aspect of things. But spent yeast, I mean, spent grain was less good of an odor as
As the straight stuff before it was filtered.
yeah. Yes.
You should try rooibos tea.
You know, I ordered your South American teas. I have some of that in my office that I was gonna use and I never have. I'm sorry, but you and I talked and it's sitting, I should either drink it or put it on a fish's nose, one or the other.
Okay, thanks. Okay, thank you, Andy. Sorry. We're doing that. I got it. So next we have Dr. Reed, who's going to be talking about thiamine addition.
Well, good morning, all. I am Amy Reed. I'm certain I've met all of you at some point in time before, maybe not in person. But today I'm going to give, and I was told I have 10 minutes. It seems like everybody else goes a bit longer. So I'll aim for 10
We have a
minutes.
little bit longer.
And then we can chat if we would like. And I'm going to give an update and focusing on the management recommendations from the study that we completed in 2022. And so I'm going to talk to you, of course, about the efficacy of thiamine treatments to alleviate thiamine deficiency in eggs of steelhead trout. And so the 30-second background on thiamine and thiamine deficiency complex, since all of us should be up to date on it, thiamine deficiency complex in fish is caused by low thiamine levels stemming from the broodstock. And these broodstock have been typically feeding on a high thiaminase diet, which depletes all of their thiamine. So there's no thiamine left in the eggs when they're ready to spawn. And so when those fry hatch, they are thiamine deficient. They can suffer from early mortality syndrome is what we typically call it. And these fish, they hatch, but they look like either side or spiral swimmers. These fish have neurologic deficiencies. They're weak fish on the bottom. They don't swim up, so they often just stay on the bottom. So there's a failure to swim up. There's a failure to go on to first feed. There's a failure to utilize yolk efficiently, and often these fish suffer from coagulated yolk, or we observe coagulated yolk in this. An inability to avoid predation, development of blindness or inability to develop vision, and death. And so fish that suffer from low thiamine, they often get picked off really quite easily in wild environments. But also the main clinical sign of thiamine deficiency is death. You need thiamine to live. You can't have no thiamine and still be alive. So we observe this, of course, in the Great Lakes. We've known this for many, many decades. We know an awful lot about thiamine deficiency complex in salmon. We also know that it's reversible and that the fish are responsive to thiamine supplementation, either by injecting the broodstock prior to spawning or by bathing the eggs at spawning in a thiamine solution. And that gets them the thiamine that they need that they didn't have in their yolk. And so thiamine deficiency complex in Oregon, we've seen this over the past couple of years. Of course, the losses of Chinook in California made headlines in 2020. We've also seen high losses of early rearing mortality in spring Chinook in Willamette Valley and Southern Oregon. We've seen high losses of coho fry in Southern Oregon, and we've detected thiamine deficiency complex in coastal steelhead in 2019 here at 3 different facilities in Oregon. This coincides with what we deem as regular or non-abnormal hatch house losses of early rearing mortality, especially in steelhead. It's very common to have a high early rearing mortality. Steelhead are hard to start. They're stressy. They just don't make it well. And if you can get them up to a certain size, especially in a hatchery, then they do well, like 100 fish per pound, then they do great. They're bomb-proof, let them go, they're great. But it's those first couple of weeks, that's just really, really hard for steelhead. And One of the questions that we asked in this project was, does supplementing with thiamine improve these early rearing losses and growth of fish reared in Oregon hatcheries? And we're very excited about what we found because it's just beautiful, and I'm really happy to talk to you about it. So we set up our experiments here at the Oregon Hatchery Research Center, where you might remember from my previous presentations, we set up fish in exposure trials, fish that were not supplemented with thiamine, so just regularly what we would be spawning year after year in Oregon hatcheries. And then fish that came from injected females prior to spawning, fish that came from non-injected females, but we supplemented with thiamine as eggs, as a soak at the day of spawning. And then we did a fourth group of fish that had thiamine from both a maternal source and an exogenous source at eggs. And we published our findings. So this was one of the take homes from this project, is that we were able to publish our findings in Veterinary Sciences, and that came out February 14th of this year. And this is what we found. We found that injecting females with thiamine significantly increased the thiamine levels of the eggs and the thiamine that is available to these fry as they're developing, as the embryos are growing and trying to utilize that yolk. Injecting the females significantly improved the thiamine levels. And so on the left, these are egg thiamine concentrations from our control fish that just were regularly returning to LC hatchery. And you can see there's three different color schemes here. Black is you have enough thiamine to have fry that survive. Red is a marginal, and maybe some of your fish might be, some of your progeny might be affected from low thiamine. And yellow is you are below the LC52 for thiamine. So that's the lethal concentration of fish. 50% of your fish will die because you don't have enough thiamine. And you can see that in the control group, we had a significant amount of fish, actually more than 50%, that didn't have enough thiamine to allow their fish to thrive. But when we supplemented the adults, we increased the average from a level of 4, which is deficient, nanograms per mole per gram of egg, up to 21. So blammo, here's all your thiamine. And that is really important, because what we also found from that, as we followed these groups in the first 8 weeks post-hatch, remember we have 4 groups, a control group that didn't see any thiamine supplementation at all, and these eggs hatched. We watched them for 8 weeks, and we charted their cumulative mortality. And these control fish, at the end of 8 weeks, had a cumulative mortality of almost 14%. And that's kind of like, okay, cool. We see that in many, many hatcheries in Oregon. That's almost considered a normal finding. And actually no alarm bells would really ring, because we know that steelhead are kind of stressy. So 14% mortality is not abnormal. Seems like it should be. However, when we charted the mortality of fish that received thiamine as a bath, we have that mortality to 6.9%, which is outstanding. Even more outstanding, wait, there's more, is that fish that got thiamine by a maternal source, by injecting the females 3 weeks prior to spawning, after 8 weeks had a cumulative mortality of under 3%. So this was extraordinary. So what we determined was that it didn't matter if you got thiamine by a bath or injection, thiamine helped reduce mortality in that first 8 weeks after hatch. So this was exceedingly exciting, but what we also found is that injections improved that even more. So keep that in mind as we talk about management recommendations. I have one more slide to show you here of data that we published in our paper. We, at that end of that 8 weeks, we measured and weighed 75 fish from each group. We got fork length and body mass. And although there were no significant differences in those 2 data points, there were significant differences when we compared condition factor. And so the condition factor of fish that got injections was significantly greater than fish that got thiamine by a bath only, or fish that didn't receive thiamine at all. And these are kind of really interesting distribution graphs. What this shows is the median condition factor, but what this is saying is that fish that got thiamine by injection utilized their feed more efficiently and grew more efficiently, but also the distribution is a little bit tighter. You can appreciate that the peaks are peakier. We have a couple of stragglers down here in the injection and bath group. But that when we look at the control group, these fish, they're not as tightly together when it comes to their size. That there were fish that's like some fish were growing more efficiently, but most of them were kind of just flopping all over the place. Whereas here, even in the injection and injectnomic group, these fish were utilizing their feed way more efficiently. Well, statistically more efficiently. So what we can talk about now, what does this mean for rearing fish in Oregon? Well, I'm going to tell you today that it is significantly changing how we're raising fish in Oregon and the Pacific Northwest. So what this means is that if we have a program that has we have a desire to increase fry survival, we can supplement with thiamine, and it will help with that early rearing mortality. So what we can do is make recommendations to inject adults with a thiamine, thiamine shot. It's just, excuse me, 1 cc in the belly, 3 weeks, at least 3 weeks prior to spawning. It can be at least 6 months prior to spawning. Or like if we cannot get our hands on the adults, and if like, let's say cohos swim up into the trap and we're spawning that day, then we can provide thiamine to the eggs as a bath on that day. And that still will help with that early rearing mortality. This is really, really important because what this can do is something that we used to think was a normal and acceptable loss now has a way to improve that mortality. It's going to inform a standard of care for steelhead rearing specifically. I mentioned coho earlier, but this study was just on steelhead. So it can inform a new standard of care that we can actually do something about this, what used to be assumed as normal losses. It can prevent fry losses in the hatch house, and it can also lower secondary disease. There'll be less carcasses around to grow fungus, to harbor bacteria, and to allow parasites to then go and infect our healthy fish. So that's going to improve the health of our fish in the hatch house troughs. It can also decrease the number of adults we need to take and the number of eggs needed. If we're going to have less mortality and less loss, we might not need to take 30, 50, 100% more eggs in order to meet our production goals. This also, supplementing with thiamine, can allow fish to grow more efficiently. And this can be really important because we know that fish that grow efficiently out-migrate more safely and return more safely. That is to say, alive. But we also have different points in life in a hatchery where your size matters, right? We already heard a little bit about that today, but we know that we can lose fish when we're grading. We can lose fish when we're marking because we have to be a certain size to get on the auto trailer. And we can lose fish when we move up a feed size from one kibble to the next bigger kibble. And if you're a straggler, you might not be able to eat these, what used to be something you can fit in your mouth. Everybody else can eat this larger size kibble, but you can't, and so you'll drop out. And so there should be less of that as the fish are more of the same size and a bit bigger. So there may be lower losses around marking feed size changes. So this has really been a whirlwind of a project. It has opened up a lot more doors and questions for further research. It has a lot of implications about hatchery, raising fish in hatcheries. I'm happy to talk about that here today. If we have some time, I'm sure you all have questions about it. But this has just been a really, really big effort by Jen, myself, Eric at Alcee Hatchery, and Freya Rowland at USG. Excuse me, is the one that did all of the HPLC analysis of thiamine levels and helped with the statistics of this paper. And she is a great collaborator at USG at CERC in Missouri, and we are continuing to work together on these types of projects. I will now open up for questions.
So what's the cost of the treatment? How economical is it?
So that's a great question. A bottle of thiamine hydrochloride has 100 mils in it, so that will treat 100 fish. That's $15. So let's say we have a 1,200 adults returning in the program, that's $100.
Is there any risk of treatment? Know that, I mean, if you just do it prophylactically, is there any risk in doing that?
There is very little risk. I can't think of a risk in doing that. We do have the risk of course, handling the females and giving an injection, which we, anytime anybody gets an injection, there's a risk of either secondary infection, lacerating an organ or something similar, bleeding, I assume, or contusions when you're giving that. There is no chance of overdosing on thiamine. It is a water-based compound, and so if you have too much of it, you just pee out the excess and your body uses what it
But if you
needs.
just use the water bath, you minimize all that. You're expecting this.
Yes and no. A water bath is a little bit more challenging. Of course, a water bath, it takes a certain amount of, you're not dosing the fish, you're dosing the water. And so depending on the volume of water that you're treating, that can get quite expensive.
Okay.
We do prescribe thiamine baths, especially as rescue. So let's say we have a group of fish that were not supplemented and hatched and are thiamine deficient, and now it's 4 weeks in and we're like, oh, we're seeing signs of thiamine deficiency. We want to treat them to rescue them. We will give, we have no choice but to give a bath to the fry at that stage. And that can be maybe $2,000 a treatment. So it's not horribly expensive, but it is a cost. So certainly injections or even baths of eggs at spawning is significantly, right? A bath of egg, that volume of water that you're treating is a gallon versus 900 gallons or 12,000 gallons if we're treating at a hatchery.
So the egg bath is not economical.
It can be economically. It does have a cost of time. So the protocols that we have right now is an hour soak, and building an hour into some of our programs can be prohibitively prohibitive. But we are working with veterinarians also in California Fish and Game to try and optimize that kind of a treatment. So instead of, let's say, 1,000 parts per million for an hour, we're toying with ideas of like 4,500 parts per million for 15 seconds. And that won't gum up a spawning day's production. The hatchery workers can still do everything they need to do in a nice flow, and it can then get the eggs the vitamin they need to develop correctly.
Your research here and your paper focused on steelhead, but of course, as you know, the USGS is doing this with bull trout. You're probably involved in that in some way. How widespread is thiamine deficiency with other salmon species?
So that's a really great question. We are investigating that right now, and COVID shut down a lot of the lab's ability to have people on station and do this analysis. So we have collected eggs from around Oregon and the Pacific Northwest, including Washington and Idaho. And what we are finding is that there is a lot of variance from a geographic perspective as to what populations of fish are showing thiamine deficiency, but we are identifying it in spring Chinook and in coho and in summer and winter steelhead. Right now, so I have data set back from probably about 26 groups of fish from 2019. And what that has shown me is that a lot of the coastal fish, coastal populations have some aspect of thiamine deficiency, whether it's 100% of the fish I tested showed thiamine deficiency, or like I have some coho groups where 2 out of the 10 individuals I tested were exceedingly low, like worryingly low, but the other 8 were fine. And if you are imagining that rearing those group of coho in a hatchery system, you might see a blip in mortality and be like, oh, some of these fish didn't do well. And in the mind of a fish culturist, you might say, oh, that was a bad female, that was a bad pairing, that was a bad spawn day. And in a sense, that's kind of correct. It is just that she might not have had enough thiamine to contribute to her progeny.
Are those egg collections all hatchery, or have you done natural?
Those egg collections are all hatchery. That's what we have access to. That's what is easiest to glean from. And what we are using, we're using them as kind of like a little peek into what's happening with these populations in the oceans. And so there is, at least right now, some extrapolation that still needs to happen in order to make these inferences between hatchery runs and wild runs. I'm not testing any wild fish because I don't have the ability to, at least in my time and ability and access, go and collect these eggs from ripe females when they're spawning And that's really what we need in order to make these comparative analyses. Claire, did you have a question?
Yeah, I love your study and I'm really excited about your results. So thank you for sharing. But I had a question. Is there any reason to expect that thiamine injections would also improve adult survival in the hatchery? And then,
I'm so glad you asked.
Just like quickly building off of that, like if you treat juveniles with eggs with thiamine by either route, is there evidence that that persists throughout their lifetime? So like when they return as adults, they would not have a thiamine deficiency?
Those are really great questions, Claire. So I have, as a clinician, if an animal is sick in my care, it gets thiamine, which is vitamin B, right? We'll give vitamin B in fluids. We'll give the vitamin B under the skin of a dog or a cat or a bearded dragon or a boa or a penguin, right? If you're sick, you get vitamin B to help you get better. And vitamin B is something that you need. And so as a management tool for adult survival, there is evidence to show that thiamine injections can mitigate pre-spawn mortality. And there was a study, I think in 2016 in Fraser River, Coho, where they were observing these adult fish that were, they called them wigglers. I think I always want to call them wobblers, but they called them wigglers. And these were coho that they were showing, they weren't shoaling normally, they weren't exhibiting normal behavior as an adult, some coho, but they were like showing these neurologic deficiencies as weakness. And when those fish were, given another week or so, they would always end up dead. And so this group administered thiamine injections to those fish, and now those wigglers completely were no longer observed. The pre-spawn mortality also declined. So there is evidence to say that thiamine is an excellent tool to promote good health in these fish that were just trying to make it. And if you've handled adult fish, you know that especially hatchery fish, we poured years of resources into them. They grow up, they outmigrate, they made it. They live in the ocean, they made it, and they came back. And we have them, and a week before spawning, they die, and it's just so heartbreaking. And if we can utilize a tool to just get them that last week so that they don't die of coloniaris, of fungus, of neurologic deficiency, anything else, just get them a little bit farther. And if thiamine can play a part in that, I would be very pleased. So as far as this study didn't look at that, but as far as management recommendations for hatchery fish and thiamine, it's definitely in my artillery of tools I'm using to help promote fish health in hatcheries in Oregon. I see many hands, so why don't you go ahead?
So I think you may have already answered this. So there's no data on thiamine levels in fish, wild fish returning. All this work has been done with hatchery fish. Did I understand that from earlier?
So I have collected samples from wild stocks, like at ALSI, I've collected from the wild stock and the hatchery stock, and have not had a chance to analyze those data yet. And I also have a couple of years of data that's in a -80 freezer. So those analyses haven't been done yet. In California, I believe that they are collecting any fish they can get their hands. So they are also analyzing the fish as they're at the mouth of the river in wild stock and hatchery stock. And then they're following those fish at the spawning grounds to see if the thiamine levels have changed. So there's a lot of projects around this. It just opens up so many questions.
And they get the thiamine from their diet, right?
They do get thiamine from their diet. Thiamine, well, so there are some differences that we can talk about. But diet can also, prey items can also be high in thiaminases. And so if you're eating a fish that's high in thiaminase, you're actively destroying your thiamine stores. But there's also can be some genetic and familial variation on how low you can be without dying. So it appears from lake trout work in the Great Lake, in the Cayuga Lakes, that some families are more tolerant of lower thiamine levels than others, which is interesting. Claire, I realized I also didn't answer the second part of your question, which is there evidence that thiamine might, supplemental thiamine might persist later on in life? And I seem to remember reading a paper, but I can't find it again, that out-migrating fish that were supplemented with thiamine still had higher levels than fish that weren't supplemented.
We have time for, I think, one more question before moving to Dr. Couch.
I was just wondering, is this deficiency, what causes it? Are we just seeing it now, or do you think it's been prevalent in the life cycle? Like you said, it's more from their diet is.
Yeah, the idea behind thiamine deficiency in Chinook and fish that actually, when I think about fish that are at risk, it's fish that are eating prey that are high in thiaminase. And on the Pacific coast, those are anchovies. And so fish that leave the Columbia-ish or leave land and head north, we typically don't see them because those are not anchovy-rich waters. But fish that out-migrate and turn left, head south, right into anchovy-rich waters. And really any fish that spend time off the coast of Northern California. So all of our coho, all of our spring Chinook are eating fish that are high in thiaminase, and they didn't used to eat that much anchovy. They used to have a very varied diet of like 20 different prey items, and they're not doing that anymore. Over the past 15 to 20 years, they now eat almost 50% of their diet consists of anchovy, whereas before it used to be. So for spring Chinook, we think that there's a really tight correlation with what they're eating and when. And so climate change might have something to do with that because they are affecting these bait fish populations, these clupeids that are high in thiaminases. Excuse me. But also it's the temperatures and currents are pushing these groups of Chinook into shallow waters at different times that they are not historically used to. And so they're having no choice but to eat these anchovy. So for Chinook and coho, the story is kind of very clear. And that seems to be a newish phenomenon. Like we are observing this most recently. But with steelhead, we're baffled. We have no idea what's going on with steelhead and low thiamine because we've observed high early rearing mortality in steelhead populations for a long, long time, right? Like it's something that has just always kind of been known that steelhead are really, really hard to start. It's like when I first started this job 5 years ago, when meeting with all of the agency fish health heads, that's one of the things we talked about is how stressed these steelhead are and what can we do about it. And we're covering them and we're salting them and we're, making their environments as less stressful as we can. But I think, steelhead aren't eating anchovy as far as we know. They have different migration patterns. We don't know what's going on with steelhead or what the mechanism is as to why steelhead are experiencing low thiamine deficiency. Is this a primary thiamine deficiency or is it something else that thiamine just happens to be helping? So these are questions that we're asking ourselves and we're working with some NOAA scientists to help us kind of try and figure that out. So doing things like stomach sampling in the oceans and still is a work in progress. So it's kind of a mystery.
All salmons are.
Well, thank you very much.
Thank you. Right, while we're loading up Dr. Couch's presentation, so we sort of migrated the 11:15 discussion period into the talks themselves. I think that's totally fine. So we'll go till about noon until the discussion is over.
Yeah,
Am I supposed to point this?
Jen-
Sure.
Jen-
It might not have been. Okay, I just wanted to make sure. So, hi, for those of you who I haven't met yet, I'm Claire Couch. I'm going to be presenting the work that I'm conducting in collaboration with Jim Peterson at the Oregon Cooperative Fish and Wildlife Research Unit. We're both based at OSU. And our project is addressing optimizing rearing conditions for Pacific salmon for hatchery production and conservation, which is very broad, but I'll get a little bit more specific as I go on. So just a quick outline of what I'm going to talk about. I'll give a brief overview and background of our project, and then talk about some updates on our deliverables and timeline. We do have some preliminary results that I will present. And then we also, our study is also a work in progress, so I'll tell you about where we're going from here. And then hopefully we'll have time for some questions. So going way back to the 2021 RFP that funded this study, one of the key questions identified by the OHRC was looking at which traits are under selection in salmonid hatcheries and how might fish culture techniques be modified to ameliorate selection. So we've heard about some really great work on genetic selection, but our approach is actually looking at selection on the gut microbiome. So the microbiome is essentially the collection of bacteria and other microbes that live on and in animals. And as I'm sure most of you are all aware from just seeing headlines over the past several years, the microbiome is critical for host health and function. We don't know a lot about the microbiome in Pacific salmon, but we have reason to believe from other study systems that early life microbiome development can have lifelong impacts on the immunity and disease resistance throughout the lifetime of a fish. So this could be affecting salmon health from juvenile outmigration all the way back to adult return and spawning. So there are a number of possible things that could drive changes in the gut microbiome, including diet, environment, antibiotic use, and host genetics. And these changes to the microbiome could affect things like disease resistance, growth, behavior, and many, many other factors that we can talk about later. So for this study, I'll just give a quick basic outline of our study design because I know I'm the last thing standing between us and the lunch break. So, but if you have more questions about the study design, I'm happy to chat more later. So essentially, we conducted an experiment at the Fish Performance and Genetics Laboratory where we held fish for 8 weeks on either a standard hatchery diet or a low lipid surrogate diet developed for the surrogate project, which is intended to mimic sort of what wild fish would be eating. And this was in Chinook salmon par. So we then also collected some samples from Marion Forks hatchery and then some wild fish from the screw trap on the North Sanian River for comparison. And our goal with this study is essentially to just understand the relationships between diet, the microbiome, and immunity in this experimental study, and then using results from the experiment and then also samples we collected from hatchery and field to understand how diet drives differences between experimental hatchery and wild microbiomes. And I apologize that my slide is a little bit cut off, so hopefully that doesn't affect the presentation too much. So our deliverables and timeline for this study. We, from the beginning, anticipated completing data analysis within 18 months of funding. So that would be this coming December that we think we will have our data analysis completed. And then at that point, we will give a presentation and report to the board. I expect that we will submit a publication in 2024. And we're on track to meet all those timelines and deliverables. So let me back up just a little bit. So I can totally sympathize with those who are trying to get sequencing done right now. I have had the microbiome data in hand for like a few days. So the stuff that I'm going to present is preliminary. Just want to let you all know that there will be a lot more interesting stuff coming out of this in the next few months, I hope, especially if I'm able to bring a student on board who can really take this data set and run with it. But so first of all, I'm going to show just some initial results from our experimental study where we held fish on the 2 different diets. And I'm just really going to focus on these 2 bar plots that are highlighted. So this was an assay we did that is just a basic measure of innate immune capacity. It's only one measure of immunity, and there are many others that we plan to run. But what it appears so far, and I presented this at the last meeting as well, which is sort of a refresher, it looks like fish on the hatchery diet have lower innate immune capacity than fish on a surrogate diet. But there's a lot of variation within these groups. And some of that could potentially be explained by differences in the microbiome. So now I'm going to show you some of our early, like hours old microbiome results. When we're looking at microbiome sequence results, one very basic measure of overall community, community health is looking at microbiome diversity. So diversity is not always good. Sometimes it means that there's something going on that is destabilizing the microbiome. So sometimes it's good, sometimes it's not good, but it is generally like an index that tends to be important in some regard when evaluating microbiome results. So with that background in mind, what we found is that microbiome alpha diversity was highest in fish in the hatchery. So these are fish collected at Marion Forks Hatchery. And the lowest average alpha diversity was in fish collected from the river. So this is from the State and Screw Trap. This sample actually includes clipped and uncooked fish. So I need to do additional analyses, sort of teasing apart the differences between those 2 groups post-release. But essentially, these are fish that are in the river, and these are fish that are in the hatchery. So like I mentioned, higher diversity is not always a good thing. One example of this is that in our recent publication, we showed that cortisol treatment, so treatment of the stress hormone, actually increases gut microbiome alpha diversity. So just saying, we don't really know what this means yet, but we're going to be further exploring it. And then looking at the results of our experiment, we found that this hatchery diet fed group was more similar in alpha diversity to the in-hatchery fish versus the surrogate diet reared group was more similar to wild fish in terms of alpha diversity. So I'm looking at microbiome composition results. I'm just going to quickly talk about what this graph means because it can be a little bit confusing to interpret if you aren't used to looking at this type of figure. So each point on this graph represents a single fish. So how close together in space the points are represents how similar they are, how similar the microbiome community as a whole is. So what we have here is the fish sampled from the hatchery are in green, fish sampled from the river are in blue, experimental fish on the surrogate diet are in purple, and experimental fish on the hatchery diet are in red. So you can see these sort of fall into 4 quadrants. And so, yeah, so this is a constrained ordination, so it's showing the maximum differences between treatments, which I can talk more about later if people are interested. So first of all, I'll just explain this difference that we see along the horizontal axis. Essentially, there is a difference between these samples that were from fish that were reared at the Fish Performance and Genetics Lab, which they're reared on well water. They're reared under very, very nice, non-stressful circumstances. So we would expect this difference versus fish that are out exposed to natural river water either in a hatchery or in a field environment. So this difference along the horizontal axis could be due to just differences in environmental conditions or environmental microbes, essentially. But then we also see this difference along the vertical axis. So there's a separation, like a very clear separation between the fish reared in a hatchery versus those reared in the river. And then that is reflected, though, to a lesser extent between fish reared on the hatchery diet in the lab and those reared on the surrogate diet in the lab. So this might not appear very exciting. It's basically what we would expect. But to me, this is actually really exciting because there are so many things that can influence the microbiome. Things that we talked about earlier, so stress, environment, host genetics. But if we're able to figure out ways to manipulate the microbiome that are straightforward, that could have really profound influences for disease resistance. And this shows that with just 8 weeks on an alternative diet, a lower lipid diet, we're able to shift the microbiome from this more hatchery-like composition to this more wild-like composition. And I forgot to click through the rest of my bullet points. Like I said, this is exciting. In terms of management recommendations, I think that will come with these next steps that I'm going to talk about. So I'm not really prepared to make firm management recommendations at this point, but I'll talk about what we're doing in the next few months. So using the microbiome results, we're going to go ahead and select some samples that we preserved from these fish to conduct additional immune assays. So we're going to look at the correlations between the microbiome and adaptive immunity, as well as immunosuppressive cytokines. So this will tell us what the relationship is between diet, microbiome, and immunity, which will be a little bit more relevant to understanding how we can use the microbiome results in a management setting. Some additional project updates that are not directly funded by the OHRC proposal, but that are relevant to our ongoing work. So we published the results of our previous study on stress hormones in the microbiome a couple of months ago. I'm happy to share that with folks who are interested. We also submitted an NSF proposal to conduct some additional microbiome and disease work that would be focused on adult fish. But it would have a lot of relevance to this study as well, because it would provide some broader context for what we're seeing in juveniles. And then we're also conducting an infection study this summer. So we're currently rearing fish on the surrogate and hatchery diets. And then in mid-July, we'll conduct an experimental infection challenge to determine whether those differences in immunity and microbiome composition that I showed you a little bit ago, whether those are actually relevant to disease resistance. So I think that if I were just doing this project out of scientific interest, I would be really excited to see those differences in microbiome composition and differences in immunity between the treatment groups. But because we're really not necessarily interested in those marginal differences for management purposes, we really need to know, like, is this actually important for hatcheries? That is the purpose of this infection study that will hopefully give us a lot more information for management. And then we're also conducting a fasting study to determine how intermittent fasting affects the microbiome. One thing that may have come to mind as you were watching my earlier slides is that, so we have this surrogate diet that may replicate wild fish microbiomes better than a hatchery diet, but it might also be more costly. So if we can achieve similar results through other means, for example, through intermittent fasting, then that could potentially be a low-cost way that hatcheries could improve outcomes for their fish. So this is kind of a pilot study. It's in the early phases, but we'll see where it goes. And then in terms of recommendations, I just want to highlight that all of this work is really new. This is a pilot study still at this point, but I think that it has really great promise for understanding sort of previously unrecognized ways that we might be able to influence hatchery fish survival and health using the microbiome. So I guess my management recommendation would be that we continue to try to understand the role of the microbiome in hatchery salmonid health. And I will hopefully be able to keep doing this research. So here's just a quick summary of what I talked about, and then I'll leave that up there, but I'm happy to take questions. Yeah.
So your way of determining the desired state of the microbiome is going to be through disease challenges with different microbiome compositions?
Yes, we're also measuring growth and immune response. But yeah, that's what I'm primarily interested in at this point.
Okay. And do you have funding for that part of the research right now? Or?
I mean, it's very inexpensive to do disease challenges. So I'm kind of just pulling things together from various sources. But no, it's not funded. I would love to get funded.
Right, it seems like that's key to interpreting this.
Yeah. Yeah.
You never got NSF, so that's.
Well, everybody always gets their first NSF proposal, right? Are there any other questions?
Yeah, so it looks like you can clearly establish a link between diet and immune function. How do you draw the link to the microbiome and immune function?
Yeah, so I will hopefully eventually be able to do this with some of the individual level data that I have. So I won't be able to causally make the connection between immunity and the microbiome, but I honestly don't think that that's really necessary for the management aspect of this. What I will be able to do is say at an individual level within a treatment group, does microbiome composition correlate with immune function? So it's not exactly a cause and effect. It won't tell us exactly the causal directionality of that, but I think that it will lay the groundwork for future studies that could tell us that causal directionality. Anybody else?
You mentioned your screw trap sample, and some of those were hatchery fish because they're fingerlip. Seems like important to use the wild fish as your sample versus the hatchery.
Yeah, absolutely. And I am still sorting through the data that was sent back to me by the sequencing center. So I'm not confident in assigning those identities quite yet, but I will get there. Sure. Yes, I was up very late last night. So, all right. Any other questions? Okay.
Thank you, Claire. I think we'll break for lunch for half hour or so. I'll be back on time for the tour. Tour's gonna take off right from here. Yeah. Sure. So we're right back here with 12:30 tour. We're gonna maybe shorten up just a little bit somewhere along the line so we can have some discussion as management recommendations before we quit. This time.
Okay, how about for the people online? For the folks online, I think we can, we're gonna stop the recording, but I'll leave the Zoom meeting on, and for people in person are gonna meet back here at 12:30 for the tour. The tour will only go till 1:30. So for the people online, we'll sign in, come back at 1:30. People in person come back at 12:30.
Oh, really?